Alright, hell yeah. So what we have here is the quick version of what I've been spending about 3 hours on. And so what we're trying to do is take a disc rolling down a vertical slope, kind of that classic problem. It doesn't fall like gravity. It falls 2/3 gravity, which is pretty cool. And so what we're going to represent it is just, hey, just like a stick, like a massless rod just out to a point mass. Can't we just do that? And then the center of this is going to be traveling with the same acceleration. So that's what we're going to show. But the other thing that we have to do is we have to take that circular disc, not necessarily it rolls or anything, but it has a mass, it has a moment of inertia. So the moment of inertia of a disk about the origin is 1/2 mr squared. But the moment of inertia about a different point, let's say we're going to say here is our rotational point, our contact point, A, that is going to be, using parallel axis, is going to be the 1/2 mr squared, just the moment of inertia of a disk, plus mr squared. So it's going to be 3/2 mr squared. So sweet. So then when we go to represent this, is kind of just, and in this, we can have the whole mass out here on a stick, it doesn't matter. But when we represent it as moment of inertia, no, we have to balance it. Having the whole mass out at this distance that we're going to find is too much. So we're going to say, hey, we're going to have, and then just in general, it's going to be 2/3 a kilogram here, and then 1/3. So if our whole thing is going to be 1 kilogram, we're going to have 2/3 up here, 1/3 here. Okay, so that's kind of what we're going to be going over. And I don't mind actually taking a little bit of time going over this. But then the video is just like learning how to learn. So this is the classic where you sum the forces in the y. So you have mg down minus the tension, and that has to equal the center of the acceleration of the center of mass, which is pretty cool. And then your other equation is torque is equal to I alpha. Now, in the end, this is what we're going to show. It's like, hey, we can easily visually represent it. So, because like right here, who the hell knows what's going on? Okay, so so we say that, so the torque about, let's say the origin is going to be the tension times this distance r. So that's the torque. I, we already said it, for a center of a circle is 1/2 mr squared. And then alpha. This is angular acceleration. So I say it's in radians per second squared. So radians times radius, anything like that gives you something normal. And so angular acceleration in radians per second squared times radius is just acceleration. So we're going to solve for angular acceleration. That's just acceleration divided by the radius. And so that's what we throw in right there. And hell, and this is just a classic solution. And then we get kind of into the cool stuff. So we say this side is T tension times the distance of radius, and then we're going to say 1/2 mr squared times acceleration over r. So if we bring this r upstairs, hell yeah, both those r's cancel, and we get tension is 1/2 ma squared. Okay, so then we throw it into this equation. So we have mg minus 1/2 ma squared is equal to ma, and then this 1/2 adds over here. So we get 3/2 ma squared. Masses can cancel, and then so we can solve for acceleration. It's going to be 2/3. Going to flip-flop that, 2/3, and that's going to be 6.6. So now this is cool. So we have the acceleration of this. It's going to be slower than free fall. And what I like to do is once I get this acceleration term, because this acceleration term is change in velocity, change in time. Well, let's just run it for a second. So after this free falls, it has an initial velocity of 0. After it free falls for a second, it's going to have a velocity of 6.6. Okay, sweet. So keep that in mind. So now what we're going to do is try to represent this as a massless rod and then a point mass out here. And so what happens with a massless rod and a point mass? It's going to fall with a gravity of 10. You do F equals ma, you have this force of mg, and then you find the mass times the acceleration of that, and you get 10, which is faster than the 6.6. But if this is farther out here, let's say it's double, and this goes 10, like a velocity of 10, or let's say, I should say this, after 1 second it's down here and it has a velocity of 10, let's say. That means the center of mass would have a velocity of 5. Oh, okay, so we need the center of mass to have a velocity of 6, so we're going to bring in this point mass. And it just happens to be that this point mass should be at 1, you know what I mean, like 1.5 times the radius. So that literally took me hours just to kind of figure out. I don't know why it took so long. But yeah, just setting it up as a general equation, we're trying to find this distance. We know just from if this has a tangential velocity of 10 meters per second, and then the equation just in general for angular speed in radians per second. Radians times radius is tangential velocity. So and in our case, our tangential velocity, our radius is going to be x. We said that this mass has a tangential velocity of 10. The radius is x. And that's going to equal 10. So we just rearrange this equation and say, you know what I mean, this omega is equal to that tangential velocity divided by x. And then I got there and I was just like, well, what the hell is this angular acceleration? Well, you go back to this if, you know what I mean, the cool thing about having the acceleration is like, hey, run it for a second. So I know that this will go from 0 to 6.6. So the center of this, after a second, will have a velocity of 6.6 meters per second. You know what I mean? So, that's cool. And if we think for a moment that, like, hey, maybe this is a pivot point, and then this point is actually has a velocity of 6.6, you know, a tangential velocity, then from this pivot point, we can kind of find the angular speed around that pivot point. And that's going to be angular speed is going to be the tangential velocity of 6.6 divided by the radius. So cool. So this omega is 6.6. You know what I mean? So, and I think I did it kind of down here. Okay, so once we have that, then we know this omega, and it's actually the x that we don't know. So I just said x is 10 divided by that 6.6. And so we get that distance of 1.5 meters, which is just 1.5 times the radius. As a generic equation, this is just always going to be 1.5 times the radius if you're going to model it like that. Okay, so we're done there, because now if I have, so I have that distance x. So then I can say, hey, I know my angular speed is 6.6, and divide by angular speed is 6.6 times 1.5. That gives me that tangential velocity that I would expect out there. Cool. And at the same time, I take that angular speed of 6.6 times just 1.5, and I see that the center of mass still travels, has a tangential speed of 6.6 meters per second. Cool, which we want. Okay, and then this problem was cool because it wasn't a function of mass. You just throw any mass out on a point, wherever its location is going to be. It's initially going to travel with an acceleration of 10. Now, like, obviously it only makes sense just for like the very instant it travels, and then saying you can run it for 10 seconds, I definitely talk about that. If this was like 100 meters, sure, you run it for a second, it's going to travel just a very minuscule amount visually. But if we're saying this is 1 meter, hell yeah. No. In a second it would travel 5 meters. It would be all the way around to there. But you can still make that leap. Okay, so now we're going to move on to showing a disk as just a, you know what I mean? Because we need this idea that mass moment of inertia from this location is a mass, you know what I mean, with the distance squared. And it has to equal that mass moment of inertia of a disk from a its pivot point on the ground has to, you know, for our example, they have to be the same. So cool. So that's where we say that the mass moment of inertia at this point is using the parallel axis theorem, it's just the mass moment for a disk, which is 1/2 mr squared plus m, and then the d, the distance is the radius squared. So we have a half plus one of these, that's 3/2. And then cool. So this is our mass moment of inertia of a disk. So if we represent it in any other way, this has to be equal. So this is just using the generic formula for mass moment of inertia. It's just like, hey, I see some mass. It has a distance away, and I'm going to square that. Now, this distance is the same distance we found in this problem, x. And so x is equal to d. And so there you go. And so now we're going to say this is going to be equal to that. So this MAD squared has to be equal to this 3/2 MR squared. And so we equate those. And so we have on this side 3/2 times 1 kilogram times 1 meter squared is equal to the mass A times 1.5 squared. Now 1.5 squared, I just said was 3/2 times 3/2, and then I just kind of canceled one of those visually. And then MA times 3/2 is equal to 1, and so I just flipped this. So MA is 2/3. So cool. So we know that that mass is 2/3, and then this other mass down here is 1/3. So we're representing this circle as has a third of the mass here and 2/3 of the mass there. So let's do that. So we have 2/3 of the mass at 1.5 times the radius, and then a third of the mass just at the origin, and it's connected by a massless rod. And it satisfies both free fall with the center of mass moving just like it should, and then also the mass moment of inertia. So then I was just like, heck yeah. Does this jive with the torques? Torque is equal to I alpha. So in our case, if we're going to represent it like this, hey, we're going to take the torques about point A. So if we do this, cool. So we're going to have 2/3 of our kilogram. So 2/3 a kilogram. And the force on that is going to be times g. So it's going to be 10 meters per second squared. And that's going to be the force in, so that's the force, and then times the distance. So basically we have the force of gravity and then the distance of 1.5. So this is going to be the force of gravity, 1.5 r. So we just did that force of gravity part. And then we have 1.5 times the radius of 1 meter. And so that's going to equal the moment of inertia. And then so we said for generic terms, hey, we have a mass at 1.5. So we have mass A, which is 2/3 a kilogram at 1.5 meters. And then this acceleration, and then so we can figure out what the acceleration term is. Okay, so a lot of things. Oh, holy Toledo. So we obviously have to square things. The generic term of mass moment of inertia is mass distance squared. So we have the mass, and then here's the distance, and we got to square that. Cool. But other than that, we're good. So we're going to cancel out that 2/3 kilograms. And then we can cancel out one of these 1.5s. And our acceleration is going to be 10 divided by 1.5, which was kind of what we solved for, kind of up here, I guess. But yeah, 10 divided by 1.5, that's that 6.6. And even right here, angular acceleration, what the hell? It's 6.6, what is this? Radians per second? Per second, you write it like this. It's a change in angular speed of 6.6 radians per second every 1 second. So if we run this for 1 second, heck yeah, our angular speed after a second is going to be 6.6 radians per second. We started with an omega of 0, so heck yeah, that was our angular acceleration. And if that is our speed, angular speed after 1 second, we should have a tangential velocity at the radius. So because omega times radians times radius, so we'll have a tangential velocity right there of 6.6 meters per second, and that jives with our idea that if we just represent this circle as dropping in free fall, heck yeah, after a second, it's going to go from 0 meters per second to 6.6 meters per second, and so it's going to have a change in velocity of 6.6. and that's its acceleration. Its acceleration is less than 10, which is gravity. So that kind of does it. And so that's my fast approach. But I don't know why this took me so long. But yeah, this video is just like, holy Toledo. You know what I mean? Just trying to come up with ideas and then just not mess them up. Just not to have false ideas in your head that don't work, but just keep pushing forward. All right, so thanks for joining me on this one. All right, hell yeah. So right now, or today, what we're going to do is we're going to simplify the rolling disc. And I thought I kind of found, you know what I mean, the solution that I wanted to. I was just like, hell yeah, this rolling disc is the same thing as like a point mass right on the ground right there. And then, you know, a bigger one right there. And then, you know what I mean, where if this is 1 kilogram, I was saying this is a half a kilogram, this is a quarter, and this is a quarter of a kilogram. And rotation, now it's just rotating or pivoting about this point. So I'm treating a circle just as a bar. And the reason why I was doing this is like because this jives with moment of inertia. So if we just have a disc that's spinning like on a stand, we have, you know what I mean, all the mass right here is not moving. The mass out here, hell yeah, it's gonna be moving tangentially. And all right, so moment of inertia for a disc is 1/2 mr squared. And cool. But then the moment of inertia, and that's about the center, you know, so right there at the center. But if this disc is rolling on the ground, and we want to know the moment of inertia at this point right here, well, now you can definitely see the disc is pivoting around this point. And so you know, we can even take the shape of the disc to be maybe something like this, and now you can even more see that it's just pivoting around this point. And what I propose is, you know, something like this, a double mass there, and now it's pivoting around that point. So this is what I'm proposing this would look like. Okay, but this video, we're going to try to tackle something harder. We're doing the disc that, or like the toilet paper roll that's unwinding itself down a wall. You know what I mean? So we're dropping a disc connected to a string, and now this is rolling vertically down a hill, and we know that the acceleration on this is 2/3 g. So compared to if we just take this same disc and drop it off a cliff, hell yeah, acceleration is going to be 10. So now where I got into the problem here was if I do that same thing and just make a pivot point and then have a mass right there and a smaller mass right there and then on a rod. Well, there was a couple things that were wrong with this, is because my pivot point actually moves downward. So we have that aspect. And well, let's see, what was the other aspect? Alright, hell yeah. And I think it's fundamentally different from this one because well, let's just run it. So what I'm proposing is we have something like this and this. You know, this is going to be in the center, and this is like that. And after we run it for, like, let's say 1 second, let's say it's really long and stuff, and so this is going to drop to here. I mean, both these, if they're just on a string, I mean, they really just want to fall. You know what I mean? They want to fall like this, just in the same location at the same time. But we know due to continuity that's not true. So this one will fall faster, and then this one will fall slower. And I guess this video is just going to show you the learning process. You know what I mean? Because even right there, I'm just like, ah, shoot. Like mentally, what I want to know is if this is similar or even synonymous with, hey, where's the center of mass? Let's say the center of mass is right there. Is this the same thing as a string with a center of mass right there and then that falling, and is that going to be my angular velocity? So the whole idea is like, hey, if you have a question, you should be able to answer it. So so instead of having this to be a half a kilogram and this is a quarter kilogram, where this is the radius and this is the radius, let's boost it up. Let's just say this is 2 and 1. And so I just want to get to solutions faster. I want to answer my own questions and get to solutions faster. So if this is 2 kilograms, this is 1. We have a force of gravity down on this of 2g, and the force of this is 1g. I mean, obviously, force of gravity is mg for both of them, but we're saying that this is 2m and this is 1m. Cool, so now we're back to kind of normal on this. Now we can use F equals ma, and we can say the force in this y direction is equal to the acceleration in the y direction. And I think that definitionally has to be the center of mass. And this is interesting. I did like the on the air hockey table. I mean, let's just take a bar, and then let's impact it just on one end with a force. You know what I mean? And let's apply that force for a whole second. I don't know. It would be the same as like impulsing it. Oh yeah, and this brings up, this is also, it's like, hey, this video is just kind of like this learning process. It's just like, well, yeah, I go to flick it. What the hell does that mean? You know what I mean? Like, basically, I would just like to have a force right here for at least 1 second. Like, that would make sense to me. And then I could do force is equal to mass times acceleration. And I could say we have a force, I don't know, like 100 newtons is equal to a mass of 1 kilogram. And then we have an acceleration. And I think this this equation would give us an acceleration of 100. I guess. Oh, my bad. I got a little carried away. Well, let's say this. We're able to simulate the same as gravity. So, you know what I mean? If this was falling under gravity, the force of gravity acts at the center of mass. I mean, it acts at every little mass, but they're all in the same direction. So then you can basically say it acts at the center of mass, and we have mg. If this is 1 kilogram, this force is going to be 1 kilogram times gravity is 10 meters per second squared, so we get 10 newtons. So yeah, let's change this. So we have 10 newtons, and so we have an acceleration of 10 meters per second squared. Now, so that's interesting that if we're able to simulate this stick in like kind of a horizontal direction, you know what I mean, where like we're looking at it from above, and it's on a frictionless, I was just thinking like air hockey table. And then we're able to have a force of 10 newtons for at least a second. What this says is that the center of mass is going to change its velocity. The velocity of the center of mass is 0. 1 second later, the center of mass is going to have a velocity of 10 meters per second. Now this problem like trips me out because it just doesn't it seems like if you put the force right at the center of mass, hell yeah, we can obviously see that this thing is going to do that, and it's not going to rotate. Oh, okay, so this is mind-blowing. Okay, because this is the preconception that I was messing up on the air hockey table. Like, let's take this thing and just put it into deep space. So just imagine, like, there's no stars around it, and I do that same thing. I put the force here. Now, my preconception was that this thing is going to rotate. You know what I mean? Because statics has told me, if we have an unbalanced force, like, you're going to have rotation. You know what I mean? Like at this point, if you pinned this point, like, or took moments just about, if we call this A and this B, if we took moments about B, and this is the length, we would, that would equal this force times length. So we're going to have, we're going to have moments about B. I think, I don't know if that even jives, but I guess my preconception was that this thing was going to rotate maybe like theoretically more than it was going to move forward, you know. And I guess even just a month ago I was just like, well, it seems like, it's like I get that it's going to move forward, but I'm just like, it's like it doesn't seem like it's going to move forward very much at all. You know, that's what I was thinking. It's just like, no, I can't see it. It looks like it's going to barely move forward, but it's going to hella rotate. And so, you know, I thought even in this scenario, after like 1 second, like the center would be here, and this thing would be hella that way. And then maybe, you know, it would look like that. And it would be rotating, and then this part would actually move that way. And I guess that's just not the case. And so, because right here I got tripped out, because it just says, well, if this center of mass, okay, so right here, like your only force is gravity, you know what I mean? And you're operating on a mass. So the F equals ma equation says you can only get a change in velocity. So if we have a force on that mass, that's going to be the change in velocity of that mass. And if it's moving like this, every particle of this mass is moving, in this case, 10 meters per second. And you couldn't have this particle move 10 meters per second and this particle move 11 meters per second. You know, you can't have that. So let's say instead of operating in the center, you do that 10 newtons right here. You know what I mean? So we have 10 newtons, that's mg, and it wouldn't do this. You know, it wouldn't go the same distance. You know, this point wouldn't go the same distance, and this would go, you know what I mean? This can't have a speed of 10, and this can't have a speed of 11, because you only have this much force to work with. But the cool thing is that the center of mass, so even if I do, yeah, this is tripping me out. Even if I put the force here, well, let's go back to putting the force here. The center of mass got to there. The center of mass was 10 meters per second. And it's good to do this. So if this is 0 meters per second, and this whole bar got up to 10 meters per second, the average velocity is 5 meters per second, and we're running this scenario for 1 second. You know what I mean? Because we have an acceleration of 10 meters per second. So after 1 second, we have this velocity. Average velocity is 5, so we want to know the distance. The distance is the average velocity, 5 meters per second, for that 1 second. So we went 5 meters. All right, so this point goes 5 meters. And now, what we're saying is that even if we move this force to the side, this 10 newtons, this location, so it's not going to be this one, but this location, the center of mass, will still go 10 meters. But then you can see it's going to start rotating this way. So what else happens? After 1 second, the center is right here, and we have the bar looking like this. Now, this didn't have to travel very far. So the speed of this one was less, and then the speed of this one was more. So if I look like right here, it looks like this, instead of going 10 meters per second, maybe went like 12.5. And this one maybe went 7.5 meters per second. So cool. And then if that's the case, and then the center went 10 meters per second. So now I can kind of average, and let's say, will this work if I do like a third of the mass there, a third of the mass? I think so. So we're going to say, we'll with F. And then this is the other thing that I have been doing, and I think it's okay to do. If I have F equals ma, and I just want to run it for a second, I know that this number on acceleration is going to be my change in velocity in units of meters per second every 1 second. So if I apply this force for 1 second, you know what I mean, I think that's very useful visually. Then my acceleration, the number on this acceleration is just going to be my velocity. If the velocity is 0, we apply a force, we're going to have an acceleration. After 1 second, that's going to be my change in velocity. So then I can just say, hey, whatever forces are on here is just equal to mass times velocity. You know what I mean? But you have to know that this is just for running it for 1 second. Okay, so we're applying a 10 Newton force. And now we broke this up. It's no longer just the center of mass moving. We have a third of it that moves. So we have a third of the mass of 1 kilogram. It moves. Its velocity is 10 meters per second. Cool. And then we're going to add it to this one, a third m, and its velocity is 12.5. And then we're going to add it to this mass. I'm sorry, this is a third. So we have a third of this mass, and its velocity is 7.5. Okay, so now this should jive, because we can factor out the 1/3 and the m, and now we just have 10 plus 12.5 plus 7.5. And 12.5 plus 7.5 is 20, so we have 10 plus 20, and that's 30. So we have 1/3 m times 30. A third times 30 is 10. And heck yeah, so now we just have m times 10, the acceleration. So the force is equal to mass times the acceleration. We have 10 newtons is equal to 1 kilogram times 10 meters per second squared. And yeah, that jives. Alright, so heck yeah. So this is fascinating that I thought I could solve this just real fast. But I play the slow game. Anytime like I'm going through something theoretical and you know something is just not 100%, you know, I definitely have to go like back to here. And so I think we proved, so now let's figure this out. Okay, so we have a string on that mass and this mass. We have, I don't like the way this is written, but we have 2 mg, and mg is our force. So we have 2 mg, and then mg is our force on these. Okay, so we know that we have a total force of 3 mg. It's the same thing we did here. We know that the whole mass is 3m, or 3 kilograms, and then we have an acceleration. But just from here, that acceleration has to happen at the center of mass. And what we're going to compare it to is the same thing of having just a 3m mass, a 3 kilogram mass, at this distance, whatever that distance is, x. Cool. So now it's I think the best way to find center of mass is to you know, yeah, it's the basic principles of statics. Statics will say that if you just have this, like we're doing the teeter-totter, so you have this 2m, 2 kilograms, and 1 kilogram, what you're trying to find is the place where this balances. So, and I do R for your reaction. So, and basic statics says, hey, we have a 2 mg force here and an mg force here, and we want this to be at some distance x, and so yeah, let's see. Okay, so our free body diagram on this, hey, we chop this and then put it into outer space. We know that we have a force here of 2 mg and a force here of mg. Okay, and now we want to And now what this says is that, hey, we have basically a net force going this way. So this thing is going to, just what is it going to do if that's the case? It's going to travel this way. And if it has a velocity 0 to start and we apply these forces, it's not only going to travel this way, it's going to increase in velocity and get faster and faster. It's not going to do anything else. It's not going to rotate, and it's not going to move sideways. Cool. Now, let's come in here, and so we know this force is like, you know what I mean? Hey, this is like 20 newtons. So just for reference, 2 mg would be like 20 newtons, because g is 10. Our mass is going to be, mass of m is 1 kilogram, and this is 2 kilograms. So we have 20 newtons there, and this force of mg is 10 newtons. Okay, so we have a total force this way of 30 newtons. So our reaction force is going to be 30 newtons the other way. Now, this is tripping me out too, because what we're going to say is, hey, let's just put this 30 newtons anywhere. Let's put it right here. So we have this, and again, this is 30, this is 20, and I'll just write that. So 20 newtons, this is 10 newtons, and this is going to be 30 newtons. So the crazy thing, and we know somewhere is the center of mass, right? Like, because this is not intuitive to me. The crazy thing is that what the static says is that, hey, now the forces this way of 20 plus 10 are going to balance with the forces that way. So if we have this scenario, and let's just draw it one more time. You know, like, I like to like put it into deep space. I'm just imagining that it's just in space, no stars around, no gravity, nothing sideways or any other way, except the forces that we put on it. So we're going to do 20 and a 10 and a 30. Now this thing will not move this direction or this direction. When it was just this, hell yeah, we could totally visualize this moving across the universe and speeding up. But the second we put that force on, well, I can't say it's not moving, because we'll get to that, but it's not moving this way, and it's not moving that way. That's crazy. It really is. It's bizarre to me, actually. So there we go. This would be the center of mass. And so this can be simplified as just like, hey, we got that, and then we have this, and then the 30 and the 20 kind of cancel, so we have 10 there, and then 10 there. 10 newtons there, 10 newtons there. Now, if this was one mass and one mass, hey, the center of mass would be in the center, 10 and 10. So it's always good to do simpler problems. And hell yeah, I could totally visualize this. This would just spin like a pinwheel. You know what I mean? So that I can visualize. But it's just so fascinating that I got that, it's going that way. Even that one was hard for me. It seems like this is like unbalanced or something where, hey, it might rotate, but it's not. Yeah, that's fascinating to me. No, is that true? No, I think no, no, like, holy Toledo. Yeah, this is so interesting. And so I'm gonna kind of even pause right here. It's just like, but yeah, this is the games that I play. It's just like, my mind tricks me or something, where even if I have this, so we're going to do this one again, 20 and a 10. Now, how do I know this thing's not spinning? Okay, hell yeah. So I think the simplest thing to do is even to break this up even farther, because we're going to do that for some of the other problems. It's like, hey, to see if there's continuity. So what I would do to this is just hey, cut this cord, whether it's a string or whatever, or a light massless rod, and say, hey, let's just have this mass of 2m, and we're applying 20 newtons on it. Cool, so now what's going to happen here? So our F equals ma says that we have 20 newtons on a 2 kilogram mass, and then the acceleration. is going to be 20 divided by 10. That's going to be 20 newtons divided by 2 kilograms. Now it's always good to do this. F equals ma, and at least do the units on it. You know, units are 1 newton is equal to 1 kilogram, and then 1 meter per second squared. So if we have newtons divided by kilograms, hey, this is just an equation. We can rearrange it anyway. So we're going to rearrange it for newtons divided by kilograms. You can just see that. We're just going to take this and put it downstairs, and that's going to give us our units of meters per second squared. So sweet. So this is going to be 10 meters per second squared. That's 20 divided by 2. Okay, so this one, and then what I always do, anytime you get acceleration, I think this is just a good strategy. Run it for 1 second. You know what I mean? Well, what is the velocity initial? Is 0, and it might not be. Some problems, hey, this might be actually having some speed, but then you're identifying some acceleration, and that's going to change. Well, just 0 is changing, and after 1 second, our velocity is going to be 10 meters per second. So sweet. So we have 10 meters per second. Our average velocity is 5, and we did that for 1 second. You know what I mean? So that's kind of what I do quickly in my head. And this moved 5 meters. Sweet. So now let's do the same thing with this mass. You know, we're going to make it totally independent. And so we have 10 there. And we have a mass of 1 kilogram. And so, F equals ma. So we're going to have 10 newtons is equal to 1 kilogram times acceleration. 10 divided by 1, so we have an acceleration of 10 meters per second squared. This velocity is 0. After 1 second, it's going to be a velocity of 10. Average velocity of 5 meters per second. It goes 5 meters. So in this scenario, after 1 second, both these went 5 meters. So we have a check on reality that this thing is not spinning. All right, and so if we're trying to analyze this one, you know what I mean, where we have a 30 and a 20, well, hey, this is going to have a 10 up, and this is going to have a 10 down. And what do we know about forces? Hey, this force, just F equals ma. Just at its basic is that you have a force, it's acting on a mass, and hey, it looks like this one is going to have some acceleration that way. You know what I mean? So you could just, you know, obviously just maybe have that particle independent, and you could see that 10 on this mass of, and this mass is 2m or 2 kilograms. And so, oh yeah, but this one's going to be slightly different, you know what I mean? So this is going to be a bigger mass. So now check this out. Yeah, this is a really good one to do, because now just the foreshadow, this won't work. You know, and hopefully I drew it better. So this is 2m and this is m. This is 1 kilogram. This is 2 kilogram from our diagram. And what we're doing is we're just putting this the resultant force in the wrong location. You know, we're not applying it at the center of mass. The first thing we're going to do is apply it over here. And if we do that, then we get this scenario where we apply this 30, this resultant, you know, the total over here. And then we get, I mean, what this is going to show is the center of mass still isn't moving. Yeah, the center of mass will always be right there. But if we try to break up this problem into 2 different chunks, separate the chord, we can see that F equals ma. For this one, we have 10 newtons. We have a mass of 2 kilograms. And so this acceleration, this is going to be 10 divided by 2. It's going to be, the acceleration is going to be 5 meters per second. So let's just, always good to run 1 second. You know, velocity is 0. And after 1 second, our velocity is going to be 5 meters per second. Average velocity is 2.5. So our distance is 2.5 meters. That's the distance that traveled upward. Now we're going to do this one independently. So this is going to be our mass of 1 kilogram. And it has 10 newtons. And we have F equals ma. So we have 10 is equal to 1 kilogram. And you can see that the acceleration on this is 10 meters per second squared. Okay, so it's... after 1 second, its velocity is 10. And its velocity initially is 0. We have an average velocity of 5. And we ran it for 1 second. So we went a distance of 5 meters. So now let's actually kind of draw that. So we're saying, hey, this is our starting point. This one moved up 2.5 meters. So we'll just go 1, 2, 3, and then we're going to say this one moved up to there. And then this one moved down 5 meters. So we go 1, 2, 3, 4, 5. Okay, so that one moved down to there. If this... Alright, hell yeah. So what the biggest hiccup visually for these rotational problems is running them for 1 second, because if we do experience some sort of rotation, so if we just have a classic this with a 1 kilogram and it's kind of, it looks like it's under free fall, its initial acceleration will be 10. I mean, that hopefully now should just be kind of obvious. But if you actually ran that for 1 second and this is 1 meter, well, you'd be going 5 meters. But if this string is only 1 meter, well, you can't go 5 meters, you know what I mean? Due to continuity, you would wrap around this circle and you'd be right there. So, so visually, we can say that the distances, this distance is going to go like 2.5 meters, and this distance is going to go 5 meters that way. Well, if we're saying this is 1 meter, well, let's call it 1,000 millimeters, and maybe we can visualize that. Well, 1 meter is 40 inches, but anyway. And then we're going to say this one moves up like 2.5 millimeters. So look at this. So this one just moves up, how about to there? You know what I mean? So let's just say that's 2.5 millimeters. And now you can kind of see it's just moving linearly. And you can get this, I mean, the relationships are going to be the same. And now this one's going to move down 5 millimeters. So we're actually just going to kind of double that. And shoot, isn't 10 millimeters a centimeter? So yeah, this one should have been a little bit more. But anyway, I think you get it. Now if this is the case, and this length, now obviously this let's say this is a massless rod or a string, that can't lengthen. So if we do move down this way and we move up this way, we actually kind of have to move in just a little bit. You know what I mean? Just so when we attach this rod to both of these, shoot, and I don't think, well, let's do it one more time with a sheet of paper so we can kind of do this visually. Just to see if we can actually get this to make sense. So I'm going to go, oh yeah, this is interesting. I mean, I can't do it to scale, but I can at least, we'll go 10 centimeters, and then so here we have that 2 kilogram, and then here we have 1 kilogram. This one moves up 2.5 millimeters. Okay, so that's where this is. And now its new center is right there. This one's new center moved 5. So it's basically right there. So now we're going to attach the new centers. And we'll see if we can visually figure out. So this was 100. This looks like 30. I mean, if I had to guess right here accurately, it would be 35. But now I kind of know this problem. You know what I mean? The light bulb went on, and the center of mass is going to be at 33.3 millimeters. If this is 100 millimeters from here to here, and then we fell 5 millimeters here, and then we went up 2.5 millimeters there. Well, now you can see visually that the rotation and the fact that this rod cannot change in length Cool. So we do rotate up, and because we rotated, you know, I mean, let's say if we are rotating about this 33.3, and I'll just do 35 for the problem. So let's say we rotate up to here. Well, now here's going to be our point, and here's going to be our point, and you can see that that yes, these two masses have to move inward for that continuity. Yeah, for that continuity to work out. All right. And what did we just show? Is this like what the hell did we just do? Oh, that's wild. That's messing with my mind. Because like we're just showing visually what center of mass is. Oh, that's trippy. Just because, yeah, we're seeing it rotate about that point. So that's interesting. So if I did this with hockey pucks, and I, you know, have the hockey pucks and then a stick connecting them on the air hockey table, and I flick this one. Now this one goes up, and we'll just do just a little bit to there. And this one more or less stays put. Is that true? Yeah, because let's do it really tiny masses, make this really long. And that's the thing, you don't want to run it for a full second. We just want to run it just, if I'm putting a little force on this, like flicking it, just after a microsecond, hey, this is right there. Yeah, this one didn't move. But it shows you where the center of mass is. Well, actually, it really doesn't. But yeah, so, well, I guess because this, yeah, I don't know. Yeah, so that would happen. Let's do the scenario where this is just twice the mass. Now, visually, what would happen if I flick this? And in this case, you have to do this. If I'm flicking with the same force, hey, this went up that distance. And so what I would do, so yeah, this would be actually more difficult than I thought, but I would snap a photo just after, you know, the same amount of time, or you could film it. You could film it in and then you know, scroll forward frame by frame. So after one frame, hey, it moved that far. So I do the same thing here. I put the force here, and so the other thing that I can do is I can just measure that distance. Okay, then I change these masses around, and well, I guess the only thing for this has to be that these two systems have to be the same. So if this is, I'm just going to say this is 4 kilograms, and let's say this is 3 kilograms and this is 1 kilogram. And by hitting this one, it moves up to that location. Cool. So then here I mark that same location, flick it with the same force, and what's going to happen here, well, in this case, it's going to be actually a quarter. Like this, this is going to move up, and so let's draw it. So this is kind of the starting place. This one ain't going to move. This one is the center of mass is going to move to there. That we know. And so the new location for this one is going to move right there. And I guess from the starting location, this moved there. Oh, that was really tiny drawn. But okay, so I think we're going to move on from that aspect. Alright, hell yeah. So back to this example where we have 2 kilograms and a 1 kilogram. And so they have a downward force of 20 newtons and then 10 newtons. And then we're trying to balance it. We put the 30 newtons there, so we're done with that. Now we're going to put the 30 newtons here. And so this is going to have a 20 Newton down, and then over to this mass, and this is going to have a 20 Newton up. Now, I guess we should run this, because it's going to show that this is going to show that that same center of mass is going to pop up. And this is the thing of learning, is just like, well, can you do it one way and then be confident that you can do it the second way and get there faster? So I'm still just going to kind of individually take this 2m, 2 kilogram, and then we have 20 on it. We do F equals ma. So we have 20 is equal to 2a. A is going to be 10 for this one. So initial velocity 0, 10, average velocity of 5. It's going to go 5 meters. Cool. Now let's do this one. So we have 20 newtons up. It's a mass of 1. So we do F equals ma. So we have 20 newtons on 1 kilogram acceleration. So the acceleration of that, oh, that's hella. You know what I mean? So that's going to be 20 meters per second. Velocity after 1 second of this one is going to be up here. It's going to be 20 meters per second. Average velocity of 10. And we're going to go 10 meters. Cool. So this one moves 10 meters. This one moves this direction 5 meters. Okay, we visually can't do that. And so we're going to do the same thing in millimeters. So we're going to go out 100. And this one is going to go down 5 millimeters. So booyah. And then this one is going to go up 10 millimeters. Or just 1 centimeter. And now we're going to connect them. And heck yeah, what do we get? You know what I mean? Hey, we get that same 33.3. That one was more accurate. So there we go. So we get 1/3 the length here, and then 2/3 the length. And so for our problem, our length is 1 meter. Okay, sweet. So now, that was interesting. That was definitely not the way that I do center of mass. I guess the way that I formally do center of mass. So let's go over that. So if this is 20 newtons on 2 kilograms, and then we have 10 newtons on 1 kilogram. What I want to do is put that, I want to put a force of 30 newtons somewhere where, and then going back to a free body diagram, I know that if this is the case, and I get these forces because there's an earth underneath. So, hey, I've identified a mass, 2m and m, and then so I can identify these forces. You know, this is my free body diagram, technically kind of in outer space, but then I just put little forces, like maybe I put little, like rocket jets that make it go this way. I'm just applying a force of 10 newtons on that mass and 20 newtons on that mass, 10 newtons on that mass. Cool, we get it. And visually, we've already shown that this thing is just going to move that way. But it's just fascinating that, yeah, gravity is that way, but some things aren't that way. Because if I had a problem that was horizontal, you know what I mean? So now we're just kind of like on a table, and I have this, and I just maybe an air hockey table, and I have that kind of that same scenario, where then I'm applying. Let's say I just apply. So I have a 2 kilogram hockey puck, and then a 1 kilogram hockey puck. And I apply 10 newtons to that one and 10 newtons to that one. Well, and they're connected by a string. Well, it's just like, well, maybe now it's not so obvious that, seems like it's balanced. Isn't this thing just going to be traveling this way? You know what I mean? Just nice and level all the way across. We have the same forces on both those. But no. So if I had this scenario where these were hockey pucks and I had to flick them, and I had to make them go the same direction, I would have to flick this one, and I could only flick, you know what I mean, for the same amount of time, putting a force for just a short period of time. I would have to flick this one twice as hard, you know what I mean, for this thing to go across. And I just think that's where, you know, like, hey, we all know force of gravity, but it's bizarre, though. It's because the force of gravity is like this perfectly portioned force for that mass. So the gravity says, oh, I have 1 kilogram mass. Guess what? I'm only going to put 10 newtons on that. You know what I mean? Hey, so that's pretty cool. You know what I mean? Hey, for gravity says, oh, I have a 20 kilogram, thing that you just dropped off a cliff. Oh, I'm going to put 20 newtons on that, and then both are going to, if we drop these both off a cliff, they're going to have the same acceleration. And I just don't think. I mean, that's where it's like one of the great videos, like of Veritasium, is going through the streets and then, saying this. And that even tripped me up. It's just like, well, is there more force on the bowling ball compared to the feather or the tennis ball that gets dropped at the same height? And it's just like, oh, never thought of that. Because doesn't it take, if I have just a hockey puck on an icy, or like a meter of steel, and we have a liquidy, icy, and I go to push this one, hell no. I'm going to have to apply a huge amount of force to get it to move the same speed as just the hockey puck. So there is that. If you want these two things to move the same speed horizontally, then the light bulb goes on. It's just like, oh yeah, no duh. Like it's going to require a huge amount of force to move things horizontally. But it's just cool that gravity perfectly portions a force for whatever mass. Yeah, it's just fascinating. It's actually a pretty wild phenomenon. Okay, so where were we? Yeah, we were trying to find center of mass. Alright, one more time. Okay, heck yeah. Yeah, it's just fascinating how it's just like, yeah, I do it one way, but then we're just doing it like a bunch of different ways. So we got 2 kilograms, 1 kilogram, we have 20 newtons, and then we have 10 newtons. And we want to apply a 30 newton force, and that was all, just so this thing doesn't move this way now. So we did that for, this thing's going to be moving, and with changing its velocity, going faster and faster this way, we're going to apply this 30 newton force. But then the other aspect, so that's the first aspect, that's going to be kind of your sum of the forces in the y direction have to equal mass times acceleration in the y, and then we're going to see no acceleration. We don't want this thing to move that way. Okay, but then the other thing is we don't want it to rotate. And so if we have a teeter-totter, that all of a sudden we put a big person and then a little person, and then we have a couple other people holding, this setup, and then they let go at the same time. What's going to happen? Well, this one's going to go that way, and it's because of this second concept, is that what's the second concept? Oh yeah. Well, it's just some of the moments, but oh man, this is tripping me out because of dynamics problems. Because the statics problem is a little bit easier. Let's say you don't drop these, so you actually have 2 people that have to hold this in place. Okay, so and they have to hold up. Like this is 1,000 newtons. That would be like 100 kilograms. So it'd be a heavy person. This is 500 newtons. That's 50 kilograms, lighter person. Okay, and then you have this kind of right in the middle. Well, and now you can kind of just get rid of this person, and then how much does this person need to hold up? Well, they have to hold up 500 newtons. Cool. And I think visually that just kind of makes common sense. But now what we're going to say is we're going to do this. Here's maybe a distance of r. We have that heavy person. But now we have something. We have this. We have like 1, 2, and we'll go out to 3. You know what I mean? Hey, so now this is 1,000 newtons, and this is 500 newtons. Now you're holding on right here. I guess the first question is like, will you have to pull down or will you have to pull up? Because maybe this was too much to handle. So we're just gonna say, how about this? Put the 500 newtons here at twice the distance. Now, you know what I mean? hey, isn't it balanced? And we kind of just know this. Yeah, you won't have to hold on. It's balanced. And it's fascinating of why that is. Yeah, and in this case, it's good to do all scenarios. Let's say we have a pivot and then kind of a steel bar. You know, it's kind of that same thing. This is our radius, and this is our 500 Newton. I'm sorry, we want to do a little bit different. Bigger bar. And then, heck yeah, this was that radius R, this was 2, and this is our 500 Newton person. And now you have to hold right here. Whoops, my person was a little bit off. That's the worst with, okay, there you go. So yeah, you're holding right here, and what are you going to have to hold? And in this scenario, you're going to have to hold 1,000 newtons, and I think that's kind of fascinating. And then if you went to right here and then held this, you would have to hold 2,000 newtons. And then get halfway, you'd have to hold 4,000 newtons. And you can see that if you get closer and closer, well, that's just going to go up astronomically. You're not going to be able to hold it. Well, with an upward force, you know, you just can't. Because of this concept of, I guess, you know, I think that kind of spells it out. You know, you're applying a turning, kind of like a moment or a couple or a torque. Those are the three. Whether it's a torque, a moment, or a couple. And all a couple is just like, hey, if I'm applying this force at this distance x, it's going to suck. But let's say I'm able to have this thing come this way, and I apply that same force over here, then heck yeah, it got twice as good. And then so the moment that I'm generating is this total distance, so it's going to be FD. So that's the definition of a couple. All right. And this obviously is just like, if I didn't apply the couple and I just had this force here and we said this distance was x, well, I would just have F times x. That's what has to equal this thing. And the leverage on this is that 500 newtons times like 2R. You know what I mean? Alright, so I guess, you know what I mean, there's no simple way around it. You have to know what the moment is, you know, what moments are. And so you have to pick a point, you know, someplace out here, that if this is your pivot point, well then you just said, if this is x, then you just said, hey, this, you know, use your right hand rule. You're going to go this distance over to this, and then it's going to have a force down of 50. And we're going to multiply those two together. So moment is R cross F. It's a fascinating thing. It's saying, hey, we're applying a force at some sort of distance, and this is how we get things done, especially like on a car. You know what I mean? Hey, we want to put what is it called? Tire iron, and we want to put a force that way, and we want to put a force that way, and then this distance, like whatever. So our couple that we're putting on, couple is the same thing as moment. The moment is going to be, in this case, well, in this case, we have two things going on. Hey, this distance is d divided by 2. So even though just couple is just easy, it's the force, it's just one of these forces times the distance. And that's kind of just like a shorthand or shortcut trick. But you can see that each of these forces is operating. So if we use the right-hand rule, heck yeah, we're going to have a positive moment of F times d divided by 2 here. And then we're going to go to this one, and we're going to have that same thing, plus F d divided by 2. And so it looks like we have 1/2 FD plus 1/2 FD. That's just FD. So there you go. Cool. Alright, so now we can find the center of mass, knowing all those things. 20, we have, 10, and from that location, a distance of x, we're going to say over here, we have a distance x, and we have a force of 20 newtons. And over here is we have an opposite, you know what I mean? So I guess you have to do this. Force, sum of the moments about any point that you want is equal to, in statics, this is going to be equal to 0. Cool. Because like force is mass times acceleration, and the definition of moment is force, basically force times a distance, let's say. So then we can say the moment, you know, substituting this into here, moment is ma times distance. It's the mass times acceleration times distance, but we don't have any, like nothing's moving, so we still don't have any acceleration. And so this side of the equation becomes 0. So if we do see a torque or a moment this way, then it has to be, sorry about that, but it has to be balanced. So if this is 1 meter, cool. So we have, we're summing the moment, so we have this 20 newtons times x. Sometimes you do the force times distance instead of, even though moment is r cross f, and it might be more useful to do the distance first, but we'll do force times distance. And then over here, we have, this is the opposite way. So if we're summing the moments, hey, we're going to say this is the positive direction, and then we're going to say this is the negative direction, and then we're going to say it's equal to 0. So that's kind of what we're doing. And this is 10 at a distance. Now this is kind of tricky. You're like, well, what is this distance? Well, if this is 1 and this is x, then this is, you know, how about 1 minus x? So if we take this distance of 1 and then we subtract that part, hell yeah. So this is 1 minus x. That's that distance right there. And so we'll have 1 minus x. Yeah, I don't think you can do it any other way. Cool. All right, so we have 20x minus 10 plus 10x is equal to 0. So we have 30x, and we're going to get this 10 to the other side is equal to 10. And our distance x is 10 divided by 30, or 1/3. So it's going to be 1/3 a meter. So sweet. So if this is 1,000 millimeters, this distance is going to be 33.3 millimeters. You know what I mean? If it's 1 meter, it's going to be 1/3, and then this is going to be 2/3 a meter over there. Okay, hell yeah. So that was just finding the center of mass. All right, this is wild. I mean, because this video really shows the learning. You know, I'm not doing it for you. I'm doing it more for me. The fact that it's just like, hey, I have this concept, and then there'll just be a little bit in my brain that's just like off or something. That's like, no, I don't believe that, or you know, so I just don't have the fundamentals just mentally, and that's what I'm kind of working on. So now I think I officially am cool with the fact that, hey, I kind of know what the center of mass is, and I understand that if I have this set up, it's going to move this way. The center of mass is going to be the one that's moving. If I have a net driving force in this direction, the center of mass is going to be moving, irrespective of the rotation. But then I think I also figured out what the rotation would be. And so do we need to do that one? Oh, that's fascinating. Yeah, I think we need to do that one more time. Yeah. So sweet. For sure. Yeah, because this is just a little bit, you know, I don't have it down crystal clear. So we have 20 newtons and 10 newtons, and I guess I should just ask a question. If I run this for 1 second, oh, never mind. In this case, there's no rotation on this. Yeah, this was one where there was no rotation. And so sweet. We actually need one where there's rotation. So what we're going to do is move on to this one. we wanted to, at the beginning of this video, hell yeah, even if this is 5 hours long, we wanted to show how a circle rolling is like a vertical rod with point masses at some location. And that is kind of what is pivoting about this point. At any given moment, like that's pivoting about that point. And this isn't quite true either, because like the second it pivots, it's actually moving its location. You know what I mean? So it's fascinating how this also might be a wrong assumption. Because here, heck yeah, we're going to try to see how this pivots, but then, heck yeah, the pivot after a little bit of time is now right here. You know what I mean? So, but one step at a time. So at least what we can do, even if our simple problem doesn't represent the more complex problem, I still think it's a good idea to always have in your mind, be like, hey, can I make a problem that what I would call simple, and then solve it, using the tools that I have. So for this, I'm going to say, heck yeah, this is going to be 2 kilograms, this is going to be 1 kilogram, and it's going to represent a disc that's 3 kilograms. Cool, so let's do that. Alright, and we'll see how many hiccups we run into. So we have 2, and then we have 1, and then kind of these two distances are the same. This is the radius right there and there. This is, we say 2m and then 1m. And this is mg. And we have 2 mg, and this is a force of mg. Alright, we have a pivot there. Now, if we separated this problem, we would see that after a second, both these want to fall at the same speed. You know what I mean? So this is the 2 mass, this is the 1 mass, and they want to be here. But because they're attached, let's say, by a lightweight rod, they're kind of a rigid body, they both can't fall that direction. They have to fall with some sort of continuity. And what that showed is that, and then, yeah, so that's where I got. That was the transition point. So what I'm going to show is like, hey, there's probably a center of mass right here. That's 1/3 r. We've already done that. That's where the center of mass is. And 2/3 r, this distance to here. And so we're going to go, and 1/3 plus r, you can say this is 3/3 r. So this is going to be 4/3. So we're going to have 4/3 r, a distance, and then we're going to put a mass that has 3m. And so this should represent this. So if we say this is 3 mg, and this is where well, I'll just show you the problem that I run into doing this. I mean, just mentally, it's just a little bit of a hiccup. If we say F equals ma, so we have 3 mg. You know what I mean? That's going to be 3 times 1 kilogram. So we have 3 kilograms times 10 meters per second squared. This is a 30 Newton mass. So we have 30 newtons. And that's going to be on a mass of 3 kilograms. And then we figure out the acceleration. Oh, so sweet. Acceleration is 10 meters per second squared. And that's what we would expect. So we would expect that this acceleration is 10 meters per second. So we do that same thing with our velocity. Our velocity is 0. After 1 second, hell yeah. Now we're just going to simulate it like it just dropped off a cliff. Our velocity, this thing's down here, and we have a velocity of 10 meters per second. Cool. Average velocity is 5 meters per second. That means we win a distance of 5 meters because we ran this for 1 second. Cool. But in this case, like, hey, if r is 1 meter, this is just a little bit more than 1 meter. But 5 meters would be, hell, somewhere down here. And if this is rotating, you know what I mean? Hey, this thing is, you know what I mean, somewhere along this circle. So so I made a video on this, just so mentally I don't see this as a hiccup, is what I can do is really drastically shorten this force. So, and yeah, this is cool. Because I'm going to drop this 3 kilogram mass off a cliff. But I'm going to say gravity, and the time frame on here is just point 1's. We're going to do. Should we do a hundredth of a second? Yeah, we'll do even smaller. I did a tenth of a second and it was small enough, you know what I mean. But we'll do a hundredth of a second. Hopefully it's not too small. But yeah, hundredth of a second. We could probably. You could probably, you know what I mean. You could probably turn on and off a stopwatch in a hundredth of a second. Have no idea. Alright, so the video that I did is I wanted to, hey, turn on gravity. So we're going to have the force of gravity turns on, and then it turns off. And we're going to turn it on, and then turn it off in a hundredth of a second. Cool. And that's the same thing. If we turn gravity on and then off in a hundredth of a second, and then we figure out our velocity after 1 second, well, what we know about F equals ma is like if something is moving with a velocity, let's say a mass moving with a velocity, and there's no acceleration, well, it's going to have the same velocity right here. So let's say we have that same mass, and then we put an acceleration on it, you know, for a hundredth of a second. Hey, let's just say it goes like 0.1 meters per second at this time, and that was just a time of a hundredth of a second. And that was we applied a force, and so F equals ma. It had an acceleration, but then we turned that off. So now it has this velocity, and then so this was a hundredth of a second, and then we just wait like a full second, you know what I mean, from the initial time we started. So we come down here to a full second, and what's its velocity? Well, it's the same. It's just 0.1 meter per second. So visually, heck yeah, you know, if you turn on a force, it's like turning on some rocket boosters just for a split second and then turn them off. Hey, you just increased your speed for that little bit, but now your speed just stays constant. So I bring this up because the other way to look at this is to have a force, because I like to think of things in like, hey, 1 second increments. Oh, and maybe I shouldn't even do this, but it would be the same thing as saying, like, so running gravity for a hundredth of a second is the same thing as dividing our mass by 100. If we do 3 divided by 100. And that's going to be 0.03. See, I should have known that. Boop, boop, and then 0.03. So we have 0.03 kilograms. Oh, whoa. Never mind. If we have a 3 kilogram, our force due to gravity, Earth underneath us, is going to be mg. That's going to be 3 kilograms times 10 meters per second squared, or we have 30 newtons. Okay, so if I take this force, and instead of running this force for a hundredth of a second, I just divide this force by 100. And we get a force of 0.3 newtons. Now I'm going to run that. I'm going to run this force on this 3 kilograms. And I'm going to run that for a full second. So I think these mental, you know what I mean, I don't know. It's probably not worth it at all. But it's just another ways to visualize kind of the same thing. It's like doing a mini problem in your head that's saying, hey, is this related? If I have a 3 kilogram mass under the force of gravity, well, what if I have that same and I'm only and I want to know its speed after a hundredth of a second, and I want to know the distance that it traveled after a hundredth of a second. Well, it's the same thing as saying, well, let's just say I have a 0.3 Newton force on a 3 kilogram mass, and we're just going to run it like it's like I went to a planet where I still have this 3 kilogram mass, but for whatever reason, the force on this 3 kilogram mass is only 0.3 newtons, which would be 100th. So this would be 100 times less than Earth's gravity. So we could probably find a tiny little asteroid, like even Pluto probably is 100 times less than Earth's gravity. I have no idea. Probably not. It's probably a little bit bigger. But you could figure out the size of an asteroid where your gravity is 100th, and you could run this experiment. And then visually you could run this experiment for a full second, and you would get the same speed out of this thing and the same distance as running this scenario just for 100th of a second. And I think visually, I don't know, I just think it's a useful tool to be able to kind of visualize both those scenarios, generating the same velocity after those times. The times are different, and generating the same different distances. This is a change in time of 1 second, and this is that 100th of a second. So let's do this one. You know what I mean? Since we kind of proved that that's the case. So we're going to have a force of 0.3 newtons, a mass of 3 kilograms, and what's our acceleration? It's going to be 0.3 divided by 3. So that's going to be 0.1 divided by 1, and so we have an acceleration of 0.1 meters per second squared. What this means is that after 1 full second, which now visually this just becomes just a lot more nice. I like running accelerations for a full second. Cool. We know that our velocity is now 0.1 meters per second. Our average velocity, we went from 0 to 0.1. So even it's hard to divide this by 2, so we do just throw an extra 0. And heck yeah, I see a 10 here, and then I can divide that by 2, and it's 0.05. So our velocity average is 0.05 meters per second, and we ran it for a full second. So that's a distance of 0.05. Now, it's also a good skill just to be able to do the same thing, you know, I mean, and maybe kind of from a more technical perspective. So we're going to use F equals ma on this. We're going to find the acceleration. So we're going to say, hey, we have 30 newtons on a mass of 3 kilograms. It looks like our acceleration is going to be 10 meters per second squared. I want to know, and this is cool because it is a constant too. And so I want to know my velocity after 100th of a second. Well, I know my velocity is going to be 10 meters per second after 1 second. So how about after 1/10 of a second? It's going to be 1 meter per second. So after 100th of a second, my velocity is only going to be 0.1 meter per second, and we arrive at the same place. So if I started here with a velocity of 0 and I ended with a velocity of 0.1 meters per second, my average velocity is 0.5 meters per second. And we win a distance of 0.05 meters. And so for this, hey, what's 0.05 meters? Multiply by 1,000, and that's going to be 50 millimeters. Oh, damn, and that was just after 100th of a second? I feel like... No. I already messed up. Alright, my bad. Yeah, maybe this isn't equivalent, you know, because, yeah, this is why I do this, because it's just so easy to, so anytime my time frame isn't just like 1 second, I kind of struggle. So, so let's do this one more time. What we're saying is that, oh, no, yeah, that is true. No, it jives. Oh, nope. I caught my hair again. Okay, so yeah, I don't know what's going on with this side. I apologize. But yeah, so that's where, yep, this one. And how could we simplify this? I mean, couldn't we just say, hey, we have some mass. We know its acceleration is going to be 10 meters per second. After a second, its velocity is 10. Its average velocity is 5, and we went 5 meters. And we did that in 1 second. So we went a distance of 5 meters in 1 second. Now we want to know what was our distance in... and no, this isn't linear. Yeah, that's kind of interesting. Yeah, you can't just say, what's my distance in 100th of a second? It's not just this divided by 100. Because if we did this, we would want to know what our change in velocity is. So yeah, let's go back to this one. I mean, it's the same one. But if we have an acceleration of 10 meters per second every second, we want to know our change in velocity after 100th of a second. So our So we're going to do that. So our velocity is going to go from 0 to 0.1 meters per second. And this is just in the time frame of 100th of a second. So that's the thing to keep in mind. So our average velocity is 0.05 meters per second. But we travel this average velocity only for 100th of a second. So the distance that we travel is this average velocity, 0.05 meters per second, just for 100th of a second. And so we have a 0.05 times 0.01. And we have a distance of, and I'm going to just multiply this by 1,000. We traveled 1/5 of a millimeter. You know what I mean? So there you have it. So if this was 1,000 millimeters, no, I guess it doesn't matter what that distance is. But yes, so if we run just free fall for 100th of a second, we're just traveling 0.5 millimeters. So that's kind of interesting. That's going to be for anything. You drop anything, and for 100th of a second, it doesn't move. It really doesn't move at all. All right, so we're going to kind of redraw these. Alright, hell yeah. So let's do anything at free fall. So now we can just kind of do the generic. We have a mass, and we know its acceleration is going to be 10. And now our time frame is just going to be 0.1 second. So our acceleration, this is going to be a change in velocity of 10 meters per second in 1 second. In 1/10 of a second, where we're just going to have a change in velocity of 1 meter per second. So we have an average velocity of 0.5 meters, but we didn't travel for a full second. That's the thing. That's like the holy Toledo. Anytime you're doing this is why it's like time squared. That's why the distance is going to be 1/2 acceleration times squared. This is where that time squared comes in. And you should never memorize this kinematic equation. I think it's garbage too. But anyway, I guess at some point, and this is going to be your initial velocity t plus your initial position. But I don't know. The only reason you should memorize is if you can recall the proof from doing it from integration, or even just doing it from this perspective. And the reason you would do a half comes from this. Hey, didn't we just half something? Look, that's the place that we halved it. We took acceleration times time. See how we just did that? We took acceleration, which was 10, multiplied it by this time factor of 0.1, and then so we got 1 meter per second. But then we had to half it to get this distance of 5 meters. I'm going to make a separate video just on that part. It's like, holy Toledo, just be like, x is equal to 1/2 at squared. You know what I mean? How the hell? And sweet. So that's where we half that. And then what do we do? So we take that 0.5. We take that 0.5 meters per second. That's our average velocity, but it's only over 1/10 of a second. So we have to multiply by 1/10 of a second to get our distance. So that's going to be 0.05. So hell yeah, so that's where that you'd multiply by the t again. That's where the squared comes from. So distance, x, 1/2 at squared. Now you know. In our problem, we didn't have any initial velocity, and our position was 0. We were setting this coordinate 0, 0, and our initial velocity is 0. Sweet. But it wouldn't be too hard just to do these intuitively too. Okay, so for this scenario, we went a distance of 0.05 meters. And then divided by 1,000. No, I'm sorry. 1 meter is 1,000 millimeters. So we get 1, 2, 3. So we get 50 millimeters. So cool. So this thing, irregardless of what this distance is in a 1/10 of a second, is going to drop 50 millimeters. Okay. So now we so what we're, for rotational problems... Alright, hell yeah. So I took a little break, and it's cool, because I think I see the light at the end of the tunnel of where we're trying to go with this. So I think we can definitely say that we have a center of mass there, And that's, we can basically, oh, excuse me, we can treat this problem where we just have all the mass right at the center. But that does increase this radius. So if this was 1 meter and this was 1 meter, for that initial circle of a radius of 1 meter that we were trying to analyze as a rolling thing around a pivot point right there, and we can just concentrate that whole mass, and we're saying the mass of this was 3 kilograms right there. And then so when we drop this in free fall, where we're using all those scenarios, like if we drop it for a second, it's going to wing around here. And obviously if this thing comes down here, oh, excuse me, gravity is not moving it in the direction of its path. It's not moving it tangential no more. Right here, hell yeah. The acceleration of gravity is moving it tangentially. So that's why we kind of took that very small change in time, just so we could reference that this thing even makes sense. And if we do that, then we actually have to be kind of careful when we're trying to find the angular in radians per second. Because if we recall, hey, we got this distance to right here in a tenth of a second. Like that was our change in time. And so when we go to do the equation on this, yeah, we'll just have to be a little bit more cautious, just knowing that this, so anyway, so what's the equation for radians? And so I have to do it this way all the time. I have to say radians times radius is something normal. I don't know, just works for me. And then so now I'm going to solve for radians. So it's going to be velocity tangential divided by r. We know our velocity tangential at this time, but again, remember that it's 0.1 seconds. It's not a second. That's why it's cool to do your problem in hey, let's run the acceleration in a second. And for this one, I'm just later on, I'm gonna pretend like I'm running it for a second, even though this thing might be way up there. But I'm just assuming that acceleration is going to be constant for that whole second. But for rotational problems, hell no. The acceleration can be constantly changing, just even after a fraction of a second. Okay, so this equation, and what did we say after a tenth of a second? Our velocity was 1 meter per second. So sweet. So our velocity right here, our tangential velocity is 1 meter per second, and then the radius in this case was 4/3 a meter. You know what I mean? Because it was this was 3/3 a meter plus a third a meter. So we have 4/3 a meter, and so we're going to divide this 4/3 a meter. Now in the break, I had to break out my calculator to do this, but you know what I mean. Obviously, just 1 divided by a fraction is the same thing as 1 multiplied by the inverse. So hell, we got 3/4. So for this, we have 3/4 of a radian. But now we have to be a little bit cautious, because if this is 3/4 of radian per second, sure, this is the speed, but this speed is at a time, this is omega at t is equal to 0.1 seconds. So we actually don't know what our omega is after 1 full second. You know what I mean? So if this is after a tenth of a second, heck yeah. Or 0.75 radians per second. After 1 full second, our omega at t is equal to 1 second will be 7.5 radians per second. So now I'll probably just kind of give up on this idea, but this is just kind of mentally. You know what I mean? The only way it's falling vertically is if that time frame is very short. So let's do that now, knowing that, and just saying who cares. We're going to have 3 kilograms. We're going to have 30 newtons. And we do our F equals ma. We're going to have 30 is equal to 3a. So we'll have our acceleration of 10. Cool. So velocity is 0. After 1 second, our velocity is 10. Average velocity is 5 meters per second. But we're just more interested in this velocity after a second. So if we know our velocity after a second, heck yeah, now we can get omega from this equation, velocity tangential divided by the radius, and we have 10 meters per second divided by that radius of 4/3 a meter. So why didn't we just do that in the beginning? Well, it's because, hey, you can't whip this thing around to there and expect that acceleration. Mentally, though, you can do that, but I'm just saying you can get there a different way just by running this thing for a very short period of time, finding the angular acceleration after only a time of 1/10 of a second or even 100th of a second, and then quantifying that would be the angular acceleration after a full second. And it's because of this. Holy Toledo! Yeah, I'm spacing out because a lot of these rotational problems, even this is nonsense. Like this value will be nonsense and this value will be nonsense. But we have 7.5 meters per second. And the reason is because, I mean, if we actually did this problem, you just wouldn't have that. But what you would have is, we know that our angular acceleration is 0 radians per second. So that's initial. And we know that we went up to 7.5. So really we want to know the angular acceleration. You know what I mean? How much is our angular velocity changing? So in this fictitious case of running this for a full second, well, hell yeah, we went from 0 to 7.5. And again, this is very similar to acceleration. Acceleration is change in velocity, change in time, dv dt. Well, angular acceleration is very similar. It's the change in angular velocity, change in time. Sometimes it's also just good to write the units. Change in radians per second per 1 second. And that's going to be dw dt. So it's interesting. If you write it kind of all three ways, now you're just ready for the calculus or the differentiation when that time comes. Okay, so we have angular acceleration. We went from 0 to 7.5 radians per second in 1 second. So we have an angular acceleration of 7.5 radians per second squared. Cool, cool. Now, if this problem was modeling a circle rolling down a vertical slope, and this was our angular now, when we model it at a pivot point here, we're saying the angular acceleration is about this pivot point. And then so how to use angular acceleration is the same way that we use tangential velocity. Because if I say, hey, this point out here is going 10 meters per second, and we're going around this, you know what I mean? Well, then I know this point right here is going 5 meters per second. That is kind of the cool thing about angular velocity is that you can figure, and this point's not moving. You know what I mean? So we have that kind of linear relationship. All right, same thing with, and if we say angular speed is 10 radians per second, we do radians times radius. That gives us something normal. That's the tangential velocity. So same thing here. If we know our omega is 7.5 radians per second, we do that times our radius of 1 meter, and we get the angular speed at this point. Sweet. Yeah. So it's very synonymous with omega. Radians per second times radius is tangential velocity. Angular acceleration times radius. Is our acceleration. So if we say 7.5 radians per second squared times 1 meter, we get our acceleration of this point, which is going to be 7.5 meters per second squared. And it's in this direction. So then we do that same thing. We run it for a second. Well, this thing is going to, if its velocity is 0, in 1 second it's going to have a velocity of 7.5 meters per second. Cool. And that's exactly what we just did. Oh, dang it. Is it? Oh, no, duh. It is. I just mixing up problems. This is 4/3 a meter. Sorry about that. So this is 4/3 a meter. So radians times radius. So 7.5 or 3/4 times 4/3. That's going to give you 1 or 10. I'm sorry, 7.5. Oh yeah, that's 30 divided by 4. So 30 divided by 4 times 4/3. That's going to give you 10 meters per second squared. So that's going to be the acceleration, apologies, 10 meters per second squared of this point. So after a second, it's going to be going 10 meters per second. And obviously, that's what we're trying to mimic as free fall. We're trying to take a rotational problem and then mimic it as free fall. Cool. And again, the only hiccup there is that you can only use that acceleration for kind of the instant it drops, maybe to about there, because it's fairly linear. But the second it starts to round this curve, hey, there is no gravity is down, there is no force actually pushing it that way. So it's just constant velocity through here. Alright, hell yeah. So now the link to do the rotational circle, because we'll actually have to do that, and what we'll find though is the center of mass is accelerating at 2/3 g. That's going to be 6.6 meters per second. So after a second, this center of mass is going 6.6 meters per second. For this problem that we just did, of assuming that a circle is like, hey, kind of a mass there and a mass there, and then maybe a mass here, but that's acting at a pivot, doesn't really count. And then that center of mass, so that's the problem that we're doing, but we see that our speed is too fast. I mean, our acceleration is, after a second, we're going 7.5 meters per second. So these two do not jive. I mean, it's fairly close. It can be a close approximation. So why I started this video is it's just like, why are linking these two things together? Why is that so hard for me? You know what I mean? I can get there, it just takes me a long time just so I don't make mistakes and stuff. But if it was a problem in a textbook that said, hey, mimic a circle as two masses or three masses, and one's about a pivot point, where So basically represent this as a bigger mass there and a smaller mass, like we've been doing, where if you added this mass and plus twice this mass, so we're just going to say this is mass A and mass B, and we did an equation that the mass of a circle, mass of C, mass of a circle would be mass A plus 2 mass B. So that's going to be our continuity. And if you did that, the center of mass of this would have an acceleration. So the acceleration of this in the y direction would be 6.6. So that, and well, we already know that's not the case. You can't do that. If this mass is, oh, I'm sorry. This mass, this would be, oh, no, that was right. Yeah, so, no, I guess this equation is generic. But now we need to come up with a number for mass A and a number for mass B where we get an acceleration of 6.6. So that is the first thing. So let's go over kind of what I want to do. So we have a rolling disk, and if we take the moment of inertia about this point, it's kind of hinged about this point, you know what I mean? So all the mass up here is moving hella. Mass here is moving normally, you know what I mean? Kind of just the actual speed of the wheel. And the masses here aren't moving at all. You know what I mean? And kind of at every point, you know what I mean? Hey, you got masses moving. So that's why we use this term second moment of mass. Well, let's not even get into that. But I mean, that's the horrible thing about second moment of mass, is that it has no... I mean, you get it, you have mass out there, but just the way that it's wrapped up in the equations is, it's kind of all discombobulated, where you don't have any sense of it, or sense of its practical meaning of like, hey, we just have, anyway. So, but if we just do it so what we know about a disk on a stand is that the I, and I think I probably messed this up in the beginning, because I ran into an error just a little bit ago. So the moment of inertia of this And all it is being like, hey, we have some sort of omega, and then we have some sort... No. And it's not even that. Holy hell. Moment of inertia is just like, hey, we have some sort of mass, and from this distance, we're taking that distance, and we're going to square that distance, and then we're going to multiply it by that chunk of mass. That's all moment of inertia is. Second moment of mass. Cool. And so for a disk, it's just going to be 1/2 mr squared. But if we want to take it about this point, if we want to see how, oh, it's hinging about this point, you should see that, hey, it's going to be more. Like just because this distance is double, when we square it, if we have 2r squared, that becomes 4r squared. You know what I mean? So these become way bigger. So so this quantity for a spinning disk that's not rolling is just 1/2 mr squared. And for this, we use parallel axis theorem to say, hey, this moment about A, the mass moment of inertia, the second moment of mass, you know what I mean, because the second part comes from the radius squared, is going to be, if it was just spinning about an axis, so that's going to be 1/2 mr squared, plus md squared. And we're saying this is the distance from the center to our point. Cool. And then that distance is just r. So we have 1/2 mr squared plus mr squared. And heck yeah. So this is 1/2 plus 1. So we have 3/2 mr squared. And so for our circle, if we just have 1 meter for the radius and a mass of 1 kilogram, we're going to have, hey, 1 squared is 1 times 1 is 1. So we're just going to have, a moment of inertia about this pivot point of 3/2. Or just 1.5. Alright, so now when we take this circle and then say, hey, we're gonna chop its mass up. It's still going to be one kilogram, but this is going to be a quarter, this is going to be a half, and this is going to be a quarter. And so now we're going to take the moment of inertia about point. And if these are point masses, well, hell, moment of inertia is just mass times distance squared. You know what I mean? So if we take the moment of inertia about this, it's like, whoa, okay, do we have a mass out there? Hell yeah. And it's a distance of radius squared. So here we go. So this is going to be, and this is why I just made this up. And it's because, look at this. A circle is all bulbous kind of in the middle. And then it doesn't have very much mass kind of at the ends. And this mass is very close to the pivot, so it won't count. And then more of the mass will be in the middle, finding your radiuses. And then less of the mass will be up top. So just doing half, quarter, and quarter kind of makes sense. And so we'll go to this one. So here's our general equation, and we have the mass of 1/2 a kilogram times the distance of r. So we'll just do 1/2, and I'll just say, hey, these are just m, just generically. So we'll have 1/2 m, and then r squared to that one. And now to this one, we have a quarter of the mass. And then the distance is going to be 2r, and we're going to square that. So now this becomes 1/4 m times 4 r squared. Sweet. So this becomes m r squared. So we have one of those. And then here we have a half. All right, booyah. All right, sweet. So we're good to go. So we have a half and 1, and that means that we have 1.5 mr squared. And then we throw in our values of the mass being 1, the total mass being 1, and then the radius being 1. So then we just have 1.5, or 3/2. And so now we have a little check on reality that this works. And you can throw in any radius and any mass, and this will be the moment, the second moment of mass moment of inertia. All right, cool, and that's important. But then we just saw that if we took this and did that same thing as a pivot and then had it fall, this velocity would be 7.5 meters per second after a second. Or you could better say its acceleration is 7.5 meters per second squared. Where we know that if we have a circle rolling down a hill, like a vertical slope on gears or unwinding itself, its acceleration is 6.6 meters per second. So this is a good representation for moment of mass, but it doesn't represent this. But that's cool because you could still change this. I mean, this isn't the only combination to represent. So if we're saying all these equal 1 kilogram, it's not the only representation. But I do want to keep it where, hey, this mass in the middle is one thing, and then these two masses on the same, that these are going to be equal to each other. But we could increase the mass in the middle. And I don't even think you do that. I actually, intuitively, I think you got to decrease this mass in the middle. And how would we prove that? Well, let's take 2 seconds, because that's the whole thing of just like getting to these little crossroads and be like, well, can we actually see what we want to do? Because what we had was these two masses rotating, and we said it's going to be 2 and 1. We put it at the center, and then we said that's 3. And then we dropped it, and it's going to obviously drop due to gravity. So it's going to go 5 meters after a second. And it's going to have, well, it's just going to have a velocity of 10 meters per second. And omega is going to be, so we have omega r is equal to tangential velocity. So omega is just that divided by r. So we're going to have 10 meters, we're always going to have 10 meters per second due to that gravity if we're simplifying it in this case. But then our radius, so that's going to be the driving factor. So it's just very fascinating to, instead of just make a huge complicated equation, go to the place that's actually the part that has the continuity. But that can be difficult to do. And we can see that this radius of 4/3, so we had 10 divided by 4/3 was 7.5. But we want it to be 6.6. So look at this. This is super easy. So 10 divided by what is 6.6. You know what I mean? And what is this as a fraction? 20/30. So I'm going to store that as x. So yeah, let's just solve this. Well, obviously you just bring the what the hell upstairs and then the divide by 6.6 down. So we got 10 divided by 6, or that 6. Yeah, so we get a distance of 3/2. And this is cool because, well, I don't know if it's cool, but anyway. So what we have is that we know that if this is our setup, we need the center of mass, let's see, to be 3/2. So this is the halfway point, this is the full way, and then if we broke this up into thirds, we need the center of mass to be here, which is cool because, you know what I mean, one simple way to do, yeah, it's fascinating because check this out. So if I have this as 2 and this is 1, the center of mass is going to be 1/3. And this is going to be 2/3. If I have this mass at 3 and this mass at 1, this distance is going to be 1/4 and this distance is going to be 3/4. If I have this mass, we'll do it one more time. Holy hell. Because this was the JEE problem. You had a 4 and 1. And then this mass was at 1/5, 1/5, and this was 4/5. And so for a multiple choice problem, you know what I mean, you don't have to spell out why you know that or how you get there. It's just very good to actually do some of these problems and see some of these patterns, you know, develop to be like, oh yeah, the center of mass. And obviously if you have 1 and 1, it's at 1/2. But I don't know. It's just, yeah, it's at 1/2. So it's interesting that if whatever masses you have, you can add them up to get like that number, and then these will kind of be flipped. You know what I mean? So this distance will be the total masses, but then this number. Like this distance will be the total masses, but then this number, and then obviously the opposite. If we wanted to know the longer distance, we're going to take, hey, we're going to add them up. That's going to be 5, and then we're going to take that number. Now, there's a few ways to get to center of mass. I like my statics method of doing finding a reaction that makes us balanced in the universe, and then so it's not rotating, so the moments are going to be the same. So yeah, so right here you have a moment of 4 divided by 5, and then over here you have a moment of 4 divided by 5. So just real fast you can kind of see that. So that's good. Cool. So here, what did we say? We needed this to be, 3 halves. So this is going to be 2 divided by 2. Oh, this has to be right in the middle. So this has to be half and this has to be half. So these actually have to be equal. Okay, so if these are equal, maybe all 3 of them are equal. But you see the problem we're going to run into is if we do that, and we do a rolling, so again, the rolling disk from point A, just a lot faster, was going to be, hey, moment of inertia of a disk, 1/2 mr squared, plus parallel axis, which is this total mass times the distance to there. So plus mr squared. So that's going to be 3/2 mr squared. So that's what we get for that. But now what we're going to say is like, well, and it's not going to work out. If we do equal masses, and we take the moment of inertia about here, okay, so, and this is just the generic equation of mass distance squared. I see a point mass and it's a distance r. So I'm going to say this is a third m, and then all these are 1/3 obviously, times r squared, and then plus a third m times 2r, and we're going to square that. So this becomes 4r squared, and we got 4/3 r squared, plus 1/3 mr squared. Sorry about the drop in the m. But yeah, so now we get 5/3 mr squared, and 5 divided by 3 is 1.6, and that's not 1.5. So we don't have a check on reality. Alright, sweet. So, and the cool thing about this, we can do whatever we want to this problem. The only thing that I want to do is just make sure that I have 3 masses. You know, if I'm doing a circle, it looks like, hell yeah, more masses in the middle, and then the same, less masses out to the end. Now, this is why I went through just kind of a lot of the basics, because I just didn't want to just go for the equation. I wanted to saturate myself into the fundamentals. So when I do this equation, I'll kind of know maybe just a little bit more about it. But now what we want is we want to have this mass, you know, its own number, and then these 2 masses to be equal. But we want to satisfy both things. We want to satisfy the fact that when this has a center of mass of just both of these, and it drops, that it will have a it'll have some sort of tangential velocity, and then the omega will be that tangential velocity divided by the radius, and that radius is going to be dictated by, you know what I mean? Hey, and this radius is just going to be 1 meter. So we're still going to keep that. We have 1 meter here, 1 meter here. But we're going to increase these. So we're going to have, 1 point. So this radius is going to be like 1 point something. But so that's going to be our check. And this has to be 6.6. So that has to check out. And then these masses, whatever they are, when we do the moment of inertia about this point, we're going to have... we're basically going to have I is equal to md squared, and so we're going to have whatever this mass is, so we're just going to call that mass A, times 1 squared, plus mass B, times 2 squared, or 4. Cool. And so just generically, this is the equations that we need to satisfy. Oh, and then this has to be 1.5. So those are our 2 equations, but for the life of me, it's just like, I just didn't think I could just say that, you know what I mean? I don't think I could have gone to find that easily. Like, my brain doesn't work very good. So, I don't know. No, I'm just making jokes, but anyway. But no, it's interesting how, like, it's so easy to trap your brain into just, like, stalemate, where you're just like, I can't think about this anymore, and I don't even know how to make correct statements, where it's just like your brain is just trying to make falsehoods all the time. And that happens a lot in math. You can either make little errors, or you can just say something that's wrong and think that's an axiom, and that is literally the worst. That's why I go through the fundamentals enough so I can use these simplifications to catch bigger errors that I'm making for harder problems. Alright, hell yeah. So let's do a fresh sheet of paper and do this. So we need, let's do the harder one. So we need this setup, and then wherever the center of mass is, you know what I mean, and we're basically kind of taking it from that x. And then our radius is going to be 1 plus x. So we definitely have that. And then we have omega r is equal to velocity tangent. And so omega is velocity tangent divided by r. And let's see. This omega, well, I mean, do we need that to be a specific value? Yes, we need angular velocity, because this is still 1 meter, and this is 1 meter. And so our tangential speed of the center, like that's our goal. You know what I mean? I'm just going to call it VR. So we want our VR after a second to be 6.6 meters per second. Like that's crucial, because that is a circle rolling down a vertical slope. Okay, and so why would we solve for omega? I forget. Oh, yeah, because we turn this into a free fall problem. You know what I mean? Hey, we just take both these masses, put it at the center of mass, and then drop it. And we know that velocity is always going to be 10. So then we have 10 divided by the radius, which is 1 plus x. And then this is going to be our, I guess that's our omega. And then we have to go back to here and say that, because that was our omega from finding the mass at the center. So we take all the mass, put it at the center, drop it in free fall. It's going, after a second, it's going 10 meters per second. But again, mentally, it's going to be all the way up here. So that's why I spent so much time going over that. So, you know what I mean, I can just, so me personally, when I get a problem like this, I can be like, hell yeah, I'm going to drop it from the center of mass. It's going to go, after a second, it's going to go 10 meters per second. And I can visually know the tangential velocity at least after a second. And I know the radius, so I can get the angular speed of this thing after 1 second. But again, it's like doubling down. It's like, well, that's still wrong. It's not going to have that angular speed, but I can still use that number to say, hey, that's going to be the accelerate. That's going to be the angular acceleration, because I'm going from 0 to that omega in 1 second. So that's why I do things in just 1 second intervals, and that's kind of just like my style currently, just so I can get an overall view of what's going on with the problem. But it's this acceleration that's the most important thing, because if I know this value, and for 1 second I can just say omega is angular acceleration, then I can find my angular acceleration, because it's not the velocity. Yeah, this is the velocity after 1 second. You know what I mean? 1 second. That's what we want to be 6.6. But like, moreover, we want the acceleration at the radius to be 6.6 meters per second squared, because it's the acceleration of a circle going down. So I'm probably just confusing the hell out of a lot of people, like just saying acceleration is velocity. But it is if you do a time frame of 1 second. But then you get a wrong answer, because that's not going to be your velocity. But it's the best way to find that instantaneous acceleration. Mentally, for me, that's the whole simplification process. So I'm glad I'm explaining that again. Okay, so, and we know this acceleration has to be 6.6, but even seeing that, like just saying the word acceleration, I don't think means much to Americans. You know what I mean? That's why people go on, what the hell is acceleration? No one knows. But But yeah, talking about velocity, we love velocity. We love driving. We love velocity. Hell yeah. And we just have, we have an intuition with velocity, that's for sure. Okay, so then, but if we get this angular acceleration, we can go back and find, and that's the thing, is like, hey, you spend so much time working with radians per second, because if I know after a second, hey, let's say it's just going 5 radians, is it 5? Or is it 10? I don't really care right now, but okay, let's just say what, no, it was 6 point, no, we really want to know that. It was 6.6, is that right? Yes, it's 6.6 radians per second, because radians times radius is our tangential velocity. So after a second, this fake circle that's just pivoted right there will be going 6.6 radians a second. That'll be its radial velocity. And then it's just really easy to be like, oh, I know it's tangential velocity, because radians per second times radius is tangential. So I can know this tangential velocity there. Well, that's going to be this times 2. So it's going to be, that's going to be 13.3, maybe? Probably not. 6.6 times 2. Yeah, 13. Ah, I did a pretty good job. And then the tangential velocity here is 6.6. So we get, I'm just saying, for me, I think we work with tangential velocity so much from angular speed that we just work so little with angular acceleration. But it works the same. If I know the angular acceleration, I know the acceleration at this point. I know the acceleration at that point is going to be double, because angular acceleration times radius, and if the radius is 2 meters, well, hell yeah, it's going to be double just AR. You know what I mean? So this is twice that. And this is how we take angular acceleration. And we know our angular acceleration is also 6.6 radians per second squared. You know what I mean? So even right here, that I was just like, oh, well, how do I know this? I knew this from the tangential velocity. You know what I mean? Because even that, humans know velocity. You know what I mean? And then I think the second thing we kind of know is like almost just angular speed. I think that's probably second. Third probably is acceleration. And then definitely for a far fourth is angular acceleration. But it's just fascinating how, we come up with an example where all those are the same. And then so we can find our angular acceleration at this point, and then let's talk about that. So now we have angular acceleration about the center of the circle, which, taken as a whole, that's the center of mass of the circle. You know what I mean? It's cool. We got that. And it's angular. So in it, the acceleration is going to be this angular acceleration times the radius. So then we would get 6.6 meters per second squared. So that would be the acceleration of this point. What does that say? Hey, this thing's not moving. And then after 1 second, the center of mass is going to have a velocity of 6.6. So that totally checks reality of what we want. You know what I mean? That's the whole thing we want. But that's going to be pivoted on what these two masses are from what equation? Probably this equation. So we want this, our angular speed, to be 6.6 radians per second. So then the only thing we need to solve for is this center of mass. And yep. And should we get a generic form for center of mass? I don't, probably not. Okay, let's take so I went there. So now let's take the circle that's rolling, or just the circle. We just want to find its I value. You know what I mean? About this point. So we have second moment of mass, moment of inertia, mass moment of inertia. 3 ways to say it, is going to be, if it was just spinning in place, 1/2 mr squared plus parallel axis to there, that's going to be the total mass times the distance to there squared, and then we get 1.5 mr squared. So cool. So if we do this in 3 chunks though, here's our radius. Radius is 1. But what we're going to do, we're going to call this mass A and this mass B. Cool. So we're going to have 1... Oh, no, and then this is just the generic, just mass distance squared. I think we use disks so much, and this half can get people tripped up. You know what I mean? But a hoop is the same thing. All the mass is at the end, so that's just going to be mr squared. And that's just the generic form. It's like, hey, we have a mass out there, a distance, and cool. And it's all, you know what I mean? Especially when we do rotational problems, hey, each of these chunks of mass has the same tangential velocity. So that makes our equations just a lot easier. Okay, so this will be just this mass, ma r squared. And then this is 2r squared. You know what I mean? So we have a distance. Our distance is going to be 2r. So d squared is going to be 2r square it, which is the same thing as 2 squared r squared. And now we can see that's 4r squared. So we're just going to do that right here. We're going to go plus 4 mb r squared. But this, you know what I mean, just the fact that in math and stuff, they always make equations visually nice. But if you actually did this equation, md squared, you would write it like this. You would do mb, and then you would square the distance, so then you would have 4r squared. So you should write it like this, where it's just like, okay, I have the mass times a distance. But I mean, just this happens a lot everywhere in physics and math, is that people just kind of write things where you got your constants out front and then your variables kind of in order, and it messes up where this might have been in one of those two parameters. Okay, so here, this equation to be O, and then what we want is that this has to be 1.5 mass total r squared. So this is our equation that has to be satisfied. And mass total, this is where I was saying that's going to be ma plus 2 times mb. Because just for my model, I want these two masses to be the same. That's it. You know, they don't have to be. But no, it would make sense that they were the same, for sure. Okay, so let's throw that into the equation. So we're going to have ma r squared plus 4mb r squared is equal to, now I'm going to have to multiply both of these by 1/2. So let's just do that right now. So that's going to be 3/2 times this. So I'm going to have 3/2 ma, and then the 2's are going to cancel, plus 3mb. Okay, so I just did that part because I don't want to do it. I don't want to write this whole thing twice. So cool. So now we're going to have, I'm just going to say this is 1.5 and this is 3. So we got 1.5. Well, and I could probably do this. That's interesting. I couldn't do that. But anyway, 1.5 ma. Yeah, some of the comments are just like, whoa, multiplying 3 times 10. But yeah, so I'll catch that because it's just like, yeah, you don't want to... I don't know. Sometimes it's good to just count on your fingers, especially for subtraction. I don't know. But then it's also good to catch yourself and just try a different method, because there's so many different methods. Anyway, cool. Let's get on with it. So we got plus 3mb. But now this whole thing is going to be multiplied by r squared. So let's just do the r squareds there. Sorry about that. But now we can combine terms. So this is going to be... well, let's get this over here. Yeah, so let's do that. So this would be 1.5 minus 1. So we're going to have 0.5 mar squared. This is going to be 4 minus 3. So we're going to have mb r squared. Oh, now what are we doing? Yeah, I feel like we're doing the same thing that we did before. Obviously, that mb is just 1/2 ma. That's not what I want. How the hell did that not work out? Oh, I guess this is just the... oh, does this have to be satisfied? No, there's no way that's the only way that can be satisfied. Damn it, it might be. Alright, hell yeah, I had to take a break because that was tripping me out. You know what I mean? I thought, for whatever reason, I thought we could just adjust these masses But no, so this equation, if we adjust this mass of A, we're definitely not going to get, because the ratio between these two, yeah, I just thought I could. So anyway, so we're gonna leave that at that. That if we're gonna do this problem, this mass B, so we're gonna call this mass C. These two masses do not. So mass B does not equal mass C, and so now we're gonna have to figure out. So I guess, yeah. So from that perspective, and I don't want to change these locations at all. I want to say that this one's right in the center, and then we have this radius, and then these are at the very ends. Cool. And so what from this page did we need to satisfy? We needed the center of mass, whatever the center of mass is, that distance, we needed this equation. So let's write that equation down and try to solve this thing. So we need 10 divided by 1 plus x. This has to equal 6.6. And this essentially was the tangential velocity divided by the radius. This is the angular acceleration. And again, this is synonymous with the angular velocity, and is synonymous with acceleration, because angular velocity times the radius is acceleration. And our radius is going to be 1 for this problem. Okay, so now we kind of have this set up, and then we have our center of mass, and this is mass C, mass B, and then mass A. Now I guess we need an equation for center of mass, and I don't mind going a little bit slower and getting a formal equation for the center of mass between these 2 points. Alright, so we have this one and we have this one. This is 1 meter. We have a force of MAG, and then here we have a force of MBG. We're going to have a resultant at some location X. So, and the resultant has to equal MA plus MB times G. Cool, you know what I mean. And then that's the sum of the forces in the Y. And then the torques, hey, about this location, we're going to have MAGX. And instead of saying this is positive and this is negative and then they're equal to 0, some of the moments about this point are equal to 0, we're just going to say, instead of positive minus negative, we're just going to say they're equal. We're going to take that negative, get it to the sides. So sometimes you can do that all in one step. So now we have this is MB, G, and I guess this is 1 minus X. So we have to say this is MBG minus MBX. No, MBGX. I'm sorry. Whoops. Okay, so MBG, that's, okay, nice. And then we get our X term. So we're going to get this over here. So we're going to get MAGX plus MBGX is equal to MBG. And we can just cancel out the G's. We're going to factor out the X. So I'm going to say X is MA plus MB. That's going to equal MB. So now we have a generic equation for this distance X. And that's going to be MB divided by MA plus MB. Cool. And I think this is the most satisfying thing about math, the fact that it works. The fact that you can just say, hey, I want to vary those things. The fact that you don't have to just like go into Excel and then try to manipulate numbers just to make it, work or something, which is also a good skill. But anyway, the fact that you can just kind of get an exact answer is pretty cool. All right, so then we have this equation. So that's it. We throw this into that equation. I think we're pretty close. The only thing that we need is, well, this will still have an equation with two unknowns, and then we'll have to have our mass total, which let's say for our problem is 1 kilogram, is going to be oh no, yeah, this is just the rotational side. I mean, we can write this down. It's going to be mass A plus mass B plus mass C. You'll definitely need this equation, but it'll be our third equation. This will be our first equation. So we're going to have 10 divided by 1 plus MB, MA plus MB. This is going to be equal to 6.6. All right, so here's our first equation. Here's our third equation. Now, the second equation says that is this one where we have we're going to take the moment of mass, mass moment of inertia. So we have this distance, and I'm sure we already wrote it down. But yeah, it's this where we need. Now in this, we just said mass total was mass A plus 2 mass B, and that's not going to be the case. And yeah, so let's write this one down. So we know that for our circle rolling, we're going to have 1/2 mass r squared. So we're going to say 1/2 mass r squared. I wrote that horribly. But 1/2 mr squared has to equal just kind of the generic md squared. You know what I mean? From this point A. So we're going to have, and this is mass B, this is mass C, and this is mass, this is mass A. Is that right? Yeah, mass A. Cool, that's the bigger mass. Looking good there. And, okay, so we're going to go up. So we're going to have mass A times radius squared. And then this one is going to be plus 4 mass B radius squared, because it's the distance is 2 times the radius, squaring that's 4r squared. So that's where this 4r squared comes from right there. Okay, and then this mass is just like mass total. Just M is mass total. Just M mass total is equal to those things. But if we actually throw this equation into there, man, we still have 3 unknowns. We don't know MA, don't know MB, we don't know MC. So then we want to have an equation that's lets us know the ratios between those. Oh, hell yeah. I love when I turn off my camera and it's just like, oh yeah, this makes so much sense. So this equation just looks sucky, but we have to solve for at least one of these. So we have to solve for MA in terms of MB or MB in terms of MA. So let's kind of just grab another sheet of paper. So we're just going to rewrite this, and let's not waste time or strokes. So we're going to take this and then multiply it up here. I guess I'll at least, I don't even want to do that once. So we're going to if we multiply this up here, we're going to get 6.6 times 6.6 MB. So we got 6.6 plus 6.6 MB divided by MA plus MB. Cool. So from here we can subtract this, and ooh, I don't want that. Don't want that as a it's messing me up. Decimal. There we go. All right. So 10 minus that, and we get, I guess it's just doing fractions on me. Uh-oh. That's all right, though. So we have 10 thirds when we minus this, and then plus, and then I guess I'm going to do, so I'm going to get this over here, 10 thirds, and then I'm going to divide by 6.6. So divide by that x, and I get a half. Sweet. So I get a half over here is equal to MB, MA plus MB. Oh, is this the same thing that's going to happen to me? This is just going to say MA has to equal 2MB. Yeah, no duh. Okay, yeah. So, yeah, we're done with this one. Yeah, no duh. MA has to equal 2MB. That's what that's going to say. And I guess, yeah, after all that, yeah, this equation is just 2MA is equal to MB. I didn't realize the simplicity of that, but yeah, that's all that's saying. So now we actually have to use this relationship into this equation. Cool. So now anywhere that we have an MB, we can switch to MA, and then we'll have MA, MB. But then this mass total will also have an MB that we can switch to MA, but it'll also have an MC. So there you go. So then we'll have this one equation. Now we can't solve it for MA or MC, but we want is a ratio. And this is fast. This is the second time just this week that it's just like, I don't have enough equations. Is this? And I don't know if people in the comments would be like, but yeah, where you don't have enough equations to solve it, but you can still get a ratio. You know what I mean? You can get, and I guess that's the definition of an equation. If you have y is equal to x plus 1, well, theoretically this is one equation with two unknowns, and you can't like solve it. You know what I mean? If you, and this is cool because this is bringing up linear algebra. My brother mailed me a textbook on linear algebra, and it'll be fascinating to do some of the problems. Like, obviously linear algebra can just be hella simple, but it's just fascinating that it's he was saying it was just a necessity to learn quantum physics. You know what I mean? You definitely use matrices, and that's about the best way to learn quantum physics. Yeah, so it's just kind of fascinating. But so I'm just glad this has come up twice where, yeah, you identify that you have one equation, two unknowns, but what can you do with this? You can say, now you know what the ratio is. You know what I mean? So if I know, let's say this is just mass A, and then this is going to be mass C plus 1. Like, this might be the ratio. That's what this might be. Okay, so this one we can rewrite and then solve it. Yeah, this has been fun, though. So we got mass total. R squared is equal to MA. And this is probably hella easy. You know what I mean? I guess I'm just going through it on camera just to show you the process. It's like sometimes, I don't know, like sometimes your brain just shuts off, and so I think it's just good to actually have like a steady flow of you know what I mean, of doing things correct and doing things right, being okay with making mistakes, and then, you know, finding your errors. And okay, sweet. So we have the mass total is going to be MA plus MB plus MC. Cool. And then we have this. So just right away, let's just throw this into this equation to get it over with. So we have, we're going to change, what should we change? What do we want to know? I mean, I guess it doesn't matter, but I'm curious. I want to know what MA is. I do. I want to know what MA is. So in our problem, this was the middle mass. I want to know that relationship to this. You know what I mean? Because, like, I don't know. Like, I didn't know if this was going to be bigger than a half. Yeah, this is fascinating. Okay, because whatever this is, this has to be half. At least we got that aspect. Whatever this is, this has to be half for our moment of inertia to be 1/2 mr squared at this point. Got that aspect. But what I don't know is if this mass, I don't know if this mass is going to be bigger or smaller. I don't know which mass is going to be bigger or smaller. So that is the fascinating thing. And I guess I don't know. Yes, it's interesting. So at the end, like, my brain can't handle that right now. Okay, so we said we wanted to know what MA is, so we're going to solve this for MB. MB is 1/2 MA, And then so anywhere where we see an MB, we're going to throw in this. So we're going to have 1/2 MA plus MA. That's going to be 1.5 MA plus MC. All right, and we're going to throw that in right here. So right here, and again, you FOIL this. We're just going to do 1/2 R squared, but that's going to be times MT. And so you can see MT is this, so we're going to take this term and then add it to this. So this is going to be 1.5. Half of that, that's going to be 3/4. So we got 3/4. And then we have MA squared. And then we have this term, which is plus 1/2 MC squared. So hopefully I did that right. And then, I forgot the R squared, though. Whoops. There we go. So we have that, and now we have MA R squared plus 4MB R squared. Oh, yeah, bummer. I should have, now I need to change this MB to 1/2 MA. So 1/2 MA times 4 is 2 MA. So this just becomes 2 MA. And let's rewrite this. So we got 0.75 MA R squared. Yeah, I don't know why I was squaring that. That was bizarre. Okay, plus, yeah, what I don't know what I was doing. But plus 1/2 MC R squared is equal to MA R squared plus 2 MA R squared. I feel like I got sloppy, so you know what I mean. Do some asterisks. I may have made a mistake, but I don't think so. I think I'm good. So now this we'll subtract over here. Let's do that. So this is going to be 1/4. So we're just going to have 1/4 MA R squared. And, oh, we have a lot. No, this is, holy Toledo. So this is 1 MA R squared plus 2 M. This is going to be 3 MA R squareds minus 0.75. So that's going to be 2.25. So we'll have 2.25 MA R squared. That's going to equal 1/2 MC R squared. Okay, so right here we can factor out a R squared. And we can even do this. Hey, let's factor out a half. How would we do that? I don't even know. Never mind. But yeah, let's just multiply this, or 1/2, we're going to multiply this 2 up here. So we're going to say MC is, so here we go. So we have 4.5 MA. Now I sure as hell made an error. I definitely, how did I mess that up? That's a bummer. Alright, let's redo that and slow it down. Because yeah, MC was supposed to be kind of small. Alright, yeah. Okay, yeah, sometimes you just have to go a little bit slower. So we have MA. Yes, MA is 2 times MB. Got that. We have mass total. I'm just going to call it M. Is MA plus MB plus MC. And so this is, I'm going to, oh, and I guess I don't know. Let's do it a different way now. And just say, nah, we tried our best finding the relationship between that. Well, let's just do it like this. So we're going to say this MA is 2 MB. So we're going to have 3 MB plus MC. That's going to be our total mass. We have, and then what equation are we putting this into? Oh. Yeah, no, I probably see my error here. Holy Toledo. Yeah, we totally messed it. Yeah, I see where we messed up. So, yeah, no duh. Because a circle, rolling from here, let's do it again, is going to be 1/2 MR squared plus parallel axis to there. So that's going to be MR squared. So this has to be 1.5 MR squared And that's what this whole equation was. And then so if we're saying it's going to be these point masses of C, B, and A, then this I will have to be mass A times the radius squared plus 4mb times the radius squared. And this has to equal 1.5 mr squared. I make this error all the time. I just said it was 1/2. You know what I mean? What the hell? So we would have got the right answer, but that was our error right there. But this is also good. This is why I do this, because it's just good to, see where you make errors and then see if you can find them fast. You know what I mean? That's the most important thing. Find your errors fast. So now we got 1.5. This is going to be the mass total. R squared is equal to, has to equal this, ma r squared plus 4mb r squared. Now let's slow it down over here. So this is going to be 1.5, and our total mass is 3mb plus mc r squared. So yeah, let's kind of foil this through. This is going to be 4.5 mb plus 1.5 mc. Cool. And then we still have that r squared. I don't want to write this again, but 4.5 mb r squared plus 1.5 mc r squared. That's going to equal this, ma r squared plus 4mb r squared. I mean, just stuff that's like should be fairly simple, but man, you can just make a lot of mistakes. And so now here I have 4.5 of these, 4 over here. I'm going to move this over here. So this will subtract. So I'm just going to have 1/2 mb r squared. Oh, and bummer. So I changed this. So we said everywhere where we have ma is 2 mb. But yeah, I didn't change this one. So let's hold off on this. Let's change this one. So this is going to be 2 mb r squared. So 2 plus 4 is going to be 6 mb r squared. So that's what we're going to have over here. So now I'll actually take this over there. 6 minus 4.5. So we're going to have 1.5 mb r squared. And then this is equal to 1.5 I'm just gonna not like this. Bummer. I feel like I'm making errors. Oh, did we not use like this continuity? That's what I thought. I thought we used this continuity, and this was a check. But yeah, this whole thing said these had to be this had to jive, but then no way. Oh, this is I think this is wrong then, because this was the whole thing where the center of mass had to be shifted, so this equation works out. Yeah, because this is just saying that these are the same. I got to take a break and then actually catch my errors. Holy Toledo. Alright, hell yeah. So I don't want to do too much work off camera, because I think I found my mistake. It was this. It was this 10 plus... I don't even know what this equation... you know what I mean? Because we found the center of mass of just... of these two. And so we did that equation... And we got that this x, this center would be mb plus, divided by ma plus mb. So just keep that in mind. But now, what were we actually doing? We were trying to get this scenario where we have, a chunk there, but it's not part of the pivot. And we have the driving forces, the two forces of gravity. We can say that that's acting at the center of mass. And then so... it's basically saying both these masses are just here, and then when we drop this, we have a free fall problem. So then we know after 1 second it's going to go 10 meters per second. We know our acceleration goes from 0 to 10, so our acceleration is 10. And then we want to know what our angular speed is after 1 second, and so then I use this equation radians times radius is something normal, tangential velocity. I solve for radians, and I get velocity tangential divided by r. And so in this case, my tangential velocity is 10, and then r is going to be 1 plus x. So then I think from this equation jives that our x is mb divided by ma plus mb. So we're going to see why or how I maybe got it. So yeah, we're just going to redo this part. So then, and then we want this to be 6.6 for sure. I don't know why I just put the 6.6 again or something. It was kind of bizarre. So we have 6.6 is equal to 10. And even there's a couple ways to do. Even right here, you could just solve for x. I could take this. I could do 6.6 times 1 plus x is equal to 10. This is going to be 6.6 plus 6.6x is equal to 10. And then I can have 10 minus 6, so I get 6.6x is equal to 3.3. And then I see that x is equal to 1/2. And so then I come back up to here, and maybe I'm just getting the same thing and we're in the same boat and I need to turn the camera off again. But we have ma plus mb. Yeah, this is bumming me out. I mean, all this is saying is that these masses have to be, oh, yeah, this is trippy. So do I need to, so is this, if I'm doing things right, let's say I'm just doing things right, that if I put these masses at 1 meter, I'm always going to get, and then I have that these are half. Oh yeah, no duh. Okay, because it doesn't matter. If these are, well, no, I thought we would actually get a tangential velocity of 7.5. If this was 2 and this was 1, didn't we get a velocity of 7.5? And so if we do this equation, it has to be less, this has to move. It can't be at a third. Oh, no, it says it has to be at a half. Oh, so right there, holy Toledo. So this x has to be a half. Okay, I get it. And if this x has to be half, these have to be equal. All right, so we have, yeah, so now we're probably totally messed up. Whereas, like, hey, we don't have two things that can be satisfied at the same time. This says that this x has to be 1/2 a meter. I think. Yeah, that's basically what it's saying. And so it has to be, and the only way for it to be half is if, well, let's run this. I guess, so we're going to have 1/2 ma plus 1/2 mb is equal to mb. So now we have 1/2 ma is equal to 1/2 mb. So yeah, so we have ma is equal to mb. So yeah, maybe, I mean, this is fascinating going through this whole process, but yeah, maybe I'm not going to get anywhere. And there isn't a way to, I can't keep these three masses in the same location and vary them, because one says that this mass has to be 2 times this mass. And then for this to work, to get an acceleration, I get that now, kind of. To get this acceleration to be 6.6, you have to, the masses have to be equal, I guess. So yeah, so let's at least run through that scenario where we have 3 equal masses. The center of mass will be right there, so that's going to be 2/3 of the 1 kilogram, and we're going to have so obviously, I mean, it comes down to the distance being this is 1 meter and this is 0.5. So this distance is 1.5 meters. Because we know after a second of free fall, it's going to go 10 meters per second. That's its tangential velocity. Omega r is equal to tangential velocity. Omega is velocity tangential divided by r. And that's going to be 10 divided by 1.5. And so we have 10 divided by 1.5. And that's going to be 6.6. So in that scenario, this is the only scenario that will give us that tangential velocity, unless we start varying these lengths. And I kind of didn't want to, that was like the last thing I wanted to do, but now I think I'm okay with, I mean, that's the only way that's going to work is to vary these lengths. And I guess then if we vary these lengths, or the position of these masses, I kind of want to keep these at the ends, and I guess I could vary this one. But yeah, maybe, I don't know, now it just doesn't become simplistic. I mean, the whole idea was like, hey, let's do something and then just turn it into a simpler problem. But I still want to get at least one continuity that works. You know what I mean? That's the whole goal of today. So I'm going to take a little break, and then we're going to go tackle it some more. Alright, hell yeah, so we're back. And, you know what I mean, I didn't take too much time, because I really want to show you the brainstorming process. Or, you know what I mean? It's like, just come up with an idea, but then spend the time going over it. So, for, a circle with a radius of 1, if we have two masses out here, we said that for moment of inertia about point A, this had to be 2 times this. But then we said also that if we're treating this as a free fall problem, and this is 1 meter, like for a radius, or it doesn't, oh, because that's the other thing, is, yeah, because this moment of inertia will work if I change the radius. But I was just thinking that, for this problem, you have to have this mass at 1.5 meters. You know what I mean? So, if that mass is at 1.5 meters, it's in free fall. Its tangential velocity is 10 divided by the radius of 1.5 gives me an omega of 6.6. So now it's just nice to be able to do that more mentally. But that's fine. It's just like, there's things, because I had this conversation, and maybe with a comment too, is like, if I'm doing coursework and stuff, like, hey, 10 years from now, when I have forgotten all the little, the quickies, what are my axioms? Definitely radians times radius is something normal. That's tangential. I think that is just a killer axiom. Because no one knows what the hell radians are. And it's just a fast way to, kind of assure yourself that that's a legit equation. And then so for us, that's going to be a tangential velocity divided by the radius, and that's going to be radians of 6.6. And that's what we want for this problem. Okay, so the first thing, and we might explore other paths, but I was just like, well, why don't we just do this? Why don't we just say a circle is a mass out here, and then some sort of other mass right here, where both these have to equal 1 kilogram. And hopefully this would be at least one check on reality that jives. I don't know why I got tripped up. There was a point here where I was just like, no, something's going to go wrong. I don't know if something goes wrong or whatever. If I'll stop and we'll go that direction. But now I think we just have a clear path, because we know that for a circle, we know that this moment of inertia about point A has to be 1.5, the total mass and just the radius of the circle. Oh, yeah, no. Now I recall. I was saying that does this only work if my radius is 1.5. I mean, because this is gonna suck if this doesn't work. Because, so let's do this moment of inertia, because we were saying that we have, 1.5, I don't know what the hell I even did. But yeah, moment of inertia about point A for a rolling circle is going to be 1.5 mr squared. And oh, you know, just back with, if this was 2x and this was 1x, it worked for all radiuses. You know, and I guess that is important, because we did a radius of 1, but hey, 1 squared, you know what I mean? Well, what if you actually have a radius of 2? So let's do that. Let's do a radius of 2 meters, and this is going to be a mass of 2 kilograms. This will be 1 kilogram, and we have a total mass of 4 kilograms total. And so for a moment of inertia, it would be 1.5 times 4 times a radius of 2 squared. So we got 4 times 4 is 16. And then we have 16 times 1, so that's 16 plus 8. That's going to be 8. That's 24. So that's what this is going to be. Now, if we come over here to this and we say, hey, we're just using the standard equation, md squared, moment of inertia is like, hey, go find a mass and what distance is it, and then square that distance. So this would be 2 kilograms times 2 squared. So that's going to be 2 times 4 is 8. And then over here, you're going to have 1 kilogram times 4 squared. So that's 16. And then plus 16. So check that out. So that jives. Both those work. But I was just like, here, man, I'm going to run into that issue of just like, well, if this radius changes, so let's try this. So we're going to come out here, and we're going to do the radius of 2 meters. So this is a meter, this is a meter. This is our point mass. Now for this scenario, it didn't matter what this mass was going to be. We just know that its velocity after a second is 10, and now, hell yeah, I can totally see this is not going to work at all. So yeah, that's so interesting. But maybe it's okay that we can actually kind of come up with another sort of equation. Yeah, the fact that this is so centered on, this won't work at all then. Because here we could vary the radius, where here this is radius dependent. If we change the radius, then we actually have to bring this mass has to be at 1.5. So yeah, that drives this problem. Oh, that is very interesting. Is that true? Holy Toledo. Yeah, because if this is on a string, and we have a velocity of 10 meters per second, that's our tangential velocity. Our radians is, radians times radius is tangential velocity, and omega is tangential velocity divided by r. That's 10 divided by 3, and yeah, we get 3.3. Alright, so I gotta totally take a break, because this actually might not work. You know, simplifying a circle rolling down a hill, well, then you're going to have an equation based on, you know, your whatever your value of your radius is. Alright, hell yeah. So this is cool, because it took only a couple seconds just to, well, about 5 minutes, but just to kind of look over this, because I was about ready to give up on it, but no, it totally works. Because we're not focused on, I was confusing, you know, like tangential velocity and, I was definitely confusing radians per second, as 6.6. I thought that was my target value, and that's not the case. For a circle rolling down a vertical, acceleration, just the acceleration in this direction is what we want. And after 1 second, we want a velocity of 6.6 meters per second of the center of this circle. And so if we treat it like a pivot from this location, like a bar, and say that bar is rotating, well, hell yeah. If we have 1 meter, sure, like we've done that. But if we increase this distance and do a larger circle, and then have it out here, well, we're saying after 1 second, this circle gets to here, let's say, and then after 1 second, this circle gets to here. Well, this bar, this shorter bar, heck yeah, it has its omega is twice. Look at this. This one only gets to there. So that's where, well, for this, when we increase this diameter to 2 meters, I said my omega was 3.3 radians per second, and I was about ready to give up. But no, that totally jives, because now the center of this will be going that same distance. The center of this circle will have a velocity after 1 second of 6.6. So it was just kind of interesting. I mean, I shouldn't be equating acceleration and velocity like that, but after a second, and if my velocity is 0 to start, my velocity after 1 second is some number, that literally, this number is the acceleration in meters per second per second. Sweet. So yeah, going back to this problem, is we can see that 3.3 radians per second. Here's the center of our circle. What's the tangential velocity of the center? That's going to be radians times radius, so we have 3.3 times 2, and that gives us that 6.6 meters per second. This is our tangential velocity after 1 second. That means we went from, this thing was not moving, to a velocity of 6.6. Therefore, we have an acceleration of the center of that circle of 6.6 meters per second squared, and that is what we find for something rolling down a hill. You know, you have this classic 2/3 g, you know, times 10, and we get 6.6. All right, sweet. So yeah, so we can continue on, thank goodness, and hopefully finish this fairly decent soon. And we're doing the simplest. Now we're just saying, hey, a rolling circle is a massless rod. Well, no, it's two things. It's still some sort of mass here, might be big or small, but then a lightweight massless rod to a mass, and this mass is going to be located at 1.5 r. So if this is the radius and this is the radius, the whole diameter is 2 r, and we want this to be at 1.5 r. So whenever this mass, the center of mass, is at 1.5 r, it generates an acceleration of 6.6 meters per second of the center of mass. So I'm so glad. Even that, I'm just so glad I have that conceptualized or whatever. And then, you know, and again, if we have a circle rolling down a hill, I'm just focusing on the center of mass, and then maybe after some time, that center of mass is right there. I should do it like this. So after just a little bit of time, that center of mass is right there. And if I'm turning this into a bar, or if I'm turning this into a chunk of mass out here that's falling in free fall, well, it's going to fall here. You know, maybe after 1 second it falls 5 meters. But then this location of the center of mass is what I see, you know, has a velocity of 6.6. And if that's its velocity, then 6.6 divided by 2, it went 3.3 meters. So now I know that this distance is 3.3. Sure, in free fall this is going 5, but then this is out at the appropriate distance, and that just happens to be, you know, 1.5 times the radius. So yeah, I think I just showed it's the ratio between a free falling object 5, and then the center of mass needing to be 3.3. So this radius is 1.5. Not confirming anything there, but I was just saying, hey, what numbers if I divide by get that 1.5? 5 divided by 3.3 is that 1.5. Okay, so now we just need to have whatever chunk of mass still makes, because we have the mass moment of inertia about a circle. You know, if we are turning this in, I guess let's get I think we can just do this on this sheet of paper. So we're turning this rolling circle into just some sort of mass at this height. And then its remaining mass will be right here. And so we know that this has to equal 1/2 mr squared. Where now I'm going to call this mass A, and then this mass B. This is going to equal whatever distance x this is. This x isn't the same thing as that center of mass x, so I should label it something different. Maybe just d. So the distance d up to there is going to be ma d squared. You know, your classic equation for moment of inertia. All right, heck yeah. And we're just going to say this is 1 kilogram. So, perfect. And the radius, just generically, we're just going to call it 1 meter. So now we just have 1/2 is equal to ma, and then whatever that distance squared is. But I don't know that distance. Shoot, and I don't know this mass. Oh, no duh. I can't do it this way. Alright, so we do have that 1/2, the mass total, ours. Oh, and why the hell am I always making this error? Man, so let's go back to the fundamentals. Is that if I have a rolling disk, especially if I'm going to make this error more than once, the moment of inertia of a disk, just rolling about like just a stand, you know what I mean? If you had a bicycle wheel on a truing stand and spun it, it's mass moment of inertia, and you wouldn't have not even spinning it. Like I shouldn't say that, spinning it. You know what I mean? Just if you're in the center, like hey, there's a chunk of mass and it's that distance away, and you do that for all points, and then you sum them up, you get this 1/2 mr squared. You use it to find motion. You know what I mean? Where the torques on it is I alpha, or linear angular moment, or what do they call it? Yeah, angular momentum is I omega. Yeah, useful parameters where you have to use moment of inertia, but it doesn't, you know, it's a property regardless of if something's spinning. Cool. All right, enough said. And then so that's just about that point. But if I want to find the moment of inertia at this point, and it makes sense, if I go down here, whoa, there's hella mass over here. I mean, well, there's mass over here, but the distance, if you square that distance, this value is just going to increase. So we have about point A is going to be, well, it's just the same thing as if it's just, and I shouldn't use the spinning, but if you're just taking about the center, mr squared plus, and then we do plus md squared. So that's going to be another mr squared, and we get 1.5 mr squared. So yeah, that's our starting value. We have 1.5 mr squared, and what we're trying to do is turn this into just some sort of generic mass, where we have this is mass A, this is mass B, and so we have mass A at some generic distance dt. So that's our first equation. Our second equation is the fact that this m, mass total, is ma plus mb. And so now we're going to have 1.5 ma plus mb r squared is equal to ma d squared. Okay, so now let's start and my radius is 1, so I'm just going to cancel that out, make it a little bit easier. And so now we have 1.5 ma plus 1.5 mb is equal to ma d squared. Okay, so we have one equation, but two unknowns. Or maybe we got three unknowns, and I still can't do anything. We'll see. Huh. Okay, no, I think it's chill. But, so we're going to get all the MAs together. So we got 1.5 MA minus MAD squared. Oh, I want to do it the opposite way, you know, because, so we got 1.5 mb, so I'm going to take this over here, plus mad squared, plus 1.5 ma. And now I'm going to factor out this ma, and so I'm going to have 1.5 mb, holy Toledo, why isn't this working? Oh no duh. Holy Toledo, I lost my brain because no, we just spent this whole time saying and confirming that this distance had to be like 1.5 times the radius. Cool. So holy Toledo. So this distance has to be 1.5 times the radius. So we could have put it in at any time, and now we'll get a ratio. So let's do that. So we have we probably should just start over. Cool. Yeah, just start nice and crisp. Because this also, sometimes if you're starting to make mistakes, you know, you can just get there just so much faster. But I'll still draw the circle A. And we have moment of inertia about A is 1.5 mr squared. And then generically, we're trying to turn it into this. But we know what D is. D is 1.5 r. And then we have mass A, but we don't know the relationship between mass A and mass B, but we do know that mass A plus mass B is equal to m. For our problem, it's just 1 kilogram. Radius is 1 meter. Cool. So even right now, since we're struggling just to get the answer, we can just say that we can just input 1 meter everywhere where we see r. So this just and 1 kilogram everywhere where we see m. So this just becomes 1.5. Hell yeah. And this becomes 1.5 for D. So now we can say that IA is 1.5, and that's equal to doing it this way, the generic way from here is just find the mass, MA, and then find the distance squared. So this is equal to MA distance squared. And now we'll throw in the fact that distance squared is 1.5. So we have 1.5 is equal to MA times 1.5 squared. So now we'll have, and we can, this is just MA times 1.5 times 1.5. And so, one of these will cancel. And then we'll have 1 divided by 1.5 is equal to MA. 1.5 is, what is that? That's 3 halves. So MA will be, so if this is 1 divided by 3 halves, that's going to be 2/3. So we have MA is 2/3. Cool. So that means that MB is 1/3. Alright, so now I think we have our solution. That a rolling disc, and maybe this only works for the no, this should work for rolling horizontally. But if we get to if we want to represent a vertically rolling disc, we would represent it as a mass here, mass B, and then a mass out here at 1.5 the radius. So yeah, that's fairly decent. And this mass out here is going to be 2/3 this mass. So if we have a 1 kilogram, this is going to be 0.6 kilograms, and this is going to be 0.3 kilograms. Or this is 1/3. If this is just the generic M, this is 1/3 M, and this is 2/3 M. Okay, so now we're going to double check that we have a check on reality. Okay, sweet. So we're going to do this mass here and come out here. And we're going to say radius is 1 meter. The total mass is 1 kilogram. So we have 2/3 m and then 1/3 m. And then our radius is right here. Our full circle would have been out here, so that's kind of what we're doing. And this distance is 1.5 radius. And so this point is going to be in free fall. It's going to have a velocity after 1 second of 10. That means omega r tangential velocity. I want to solve for omega. That's tangential velocity divided by r. That's going to be 10 divided by 1.5. Cool. That's going to be your 6.6. And this is in radians. Is that even true? 10 divided by 1.5. Yep. And then so this is my angular velocity. And so I can find the velocity of the center of the circle. That's kind of what I want to do. Find the velocity of the center, and that's going to be 6.6 times my radius of 1. So cool. The velocity of the center is 6.6 meters per second. And I know it started at 0 meters per second. And so I know its angular just know the acceleration of that circle is 6.6 meters per second. And that checks. That's going to be 3/2 g, which is 6.6. Cool. All right, so there's the check there. But also, we know that a circle, the I about this point A, is I about A is going to be I about the origin plus parallel axis, mass times distance squared. And then for our representation of 1.5 r, we have 2/3, and so we're going to say, and just generically, if this is the disk that we're analyzing of the 1 kilogram with a radius of 1 meter, this is going to be 1/2 mr squared, generically just for a disk, plus parallel axis will be mr squared, so that gives us 3/2 mr squared. So now we're saying, hey, what is the moment of inertia about this system about point A? You know what I mean? And this is two separate problems. It doesn't matter if you mentally link these together or if they're true or not. You're just saying, hey, I came up with a different setup. Does it have the same moment of inertia? Like, go. There's the problem. So we're just going to do it generically. And generically, moment of inertia is mass times distance squared. And so we have the mass of 2/3 times 1.5. And this is 1.5 r squared. So we get, and then 1.5 is 3/2. And so what we're going to get is, 2/3 times 3/2 times 3/2 times r squared. So that's all I did. I did 1.5 squared and then r squared. And I saw that 1.5 is 3/2, and I squared that. And I just did it twice. I just said this was that twice because now I can see one of them cancels, and then I get 3/2 r squared. And, oh, did I not do the mass? I mean, this one, the mass was 1, and so I would have had 3/2 r squared if the mass was 1. But, yeah. So there you go. Oh, and then I already put the mass in. So I said this was the mass, and then distance squared. But my mass of this setup is different. It's just 2/3. But yeah, but you get the same value. Okay. So I shouldn't have written this one like this. I should have just totally spelled it out. So the actual moment of inertia of this is 1/2 times the mass of 1 kilogram times the radius, which is 1 meter squared, and this, plus parallel axis, the mass of 1 kilogram times the distance. All right, so, yeah. So the parallel axis is 1 kilogram times the distance is of 1 meter squared. So this is 1 and this is 1/2. So I get 1.5. So that's just the value for that. I come down here and I say this is 1.5 r is just 1.5 meters. So I say this is the mass of 2/3 a kilogram times the distance of 1.5 meters squared. And this is going to give me 1.5 squared times 2 divided by 3 is 1.5. So there you go. So there's a check on reality. And hopefully I'm going to do, kind of the polished version. Because I'm just surprised this takes me this long to get there. You know what I mean? Because I make a mistake and then I have to go back. And I just don't see it. So that's just the fascinating thing about being a better problem solver. And I'm okay with not seeing it. You know what I mean? That's the thing. That's why I do my style. And I think that's why I'm doing well, like, on the internet. Is just like, hey, I don't mind, like, just taking these tiny baby steps, like, and then trying not to make mistakes. Maybe making a mistake, you know what I mean? Doing, like, the 1 step forward, 2 steps back. But then, hell yeah, just continuing that process to where you can just make easy layups. So the difference between actually getting this, like, aha moment of, like, oh yeah, you know what I mean, just those aha moments are very small steps, you know what I mean, they're just like no does, compared to finding little magic tricks and then using magic tricks. I don't know, that's just the thing with math and even physics is it's cool to learn tricks, and you need to, but then also just seeing if you can get there from just a basic perspective. But I get it. Like, this isn't a simpler way to do it. It's just a way where your mind can always wrap your head around, hey, a free-falling object. And I think that's the most important thing about the way I want to learn rotational problems. It's like I want to learn them from just the perspective, kind of that. So I think I'm done. And so, hell yeah, thanks for joining me, and that's a video.